work? Alrighty, I'll wait a couple more minutes and then start, I think. Is it 10? It's 9:59. Thanks for coming. This is the Geospatial Mini Symposium. I am Anshul Singhvi. I do a bunch of work in the Julia Geo ecosystem. Um, yeah, great to have you guys here. So before I start my talk, I just wanted to say a couple of things. This particular session, I think, is coming in at a time when we have a lot of change in the ecosystem. We have, the rise of AI and AI-based coding tools. We have, so I think much of this session is going to be on work that we have done and want to combine as well. So things will change rapidly, even just immediately after the session, for instance. Ah, perfect. Thank you, Valentin. um, oh, so this has multiple. Okay, sweet. Yeah, so I'll start out. So I wanted to sort of discuss briefly and give an introduction to discrete global grids, or DGGS is the abbreviation. Um, so what are these things? Well, a discrete global grid is just a mosaic of cells. Sorry. Oh, is it not? Oh, that's not good. It seems to be saying that it's mirroring. Let me try again. No? Huh. You know what? No, the dongle. Oh, I'll try it with the dongle, see what happens. Oh dear. Well, this was working not so long ago. Yeah, I was in the fort earlier. It was. Nice. Well, there we go. Oh, I'll unplug it from the charging. Maybe that helps. Okay, now we're back to it's trying to share, but it's. All right. Well, I'll keep talking while we figure this out. So a discrete global grid is just some set of grid cells which covers the globe, and they could be any kind. That you could have rectangles, hexagons, pentagons, so on and so forth. The simplest one that we all know is the longitude-latitude grid, right? There you have. Um, oh, is the audio not coming through? Ah, okay. I'll just do that. So simplest one is a longitude-latitude grid where you have, this is the standard map of the Earth. See, right? Okay. Still not working. Oh, it is? Okay. So we have a little continent here, right? But the problem with this is that the Earth is, in fact, a sphere. This may be slightly controversial, but the problem is we've got this little point right over here, which is translating to this relatively large line. So you get space, space is distorted, right? These grid cells are very small over here, and then grid cells around the equator are by contrast very large. Um, so I had some very cool graphics that would have shown this. Um, but you can sort of imagine, your regular globe with your regular longitude latitude lines. Um, One of probably the first DGGSs or grid systems that came about, or one of the first big ones that people knew about, was Uber's H3 grid, which was a bunch of hexagons. Um, I'll try and turn my laptop around here. I don't know how many of you guys can see this. Um, but you can sort of see that uh, this ended up taking this Earth and tiling it with hexagons. And the nice thing about hexagons is, so the nice thing about, first of all, working directly on the sphere is that with these hexagons live natively on the sphere. So you didn't have the problems of, certain cells are are completely tiny and some certain cells are gigantically huge. Um, but these, oh, I drew a pentagon here. Why did I do that? Um, oh, oh no. Everyone gets 1 second to view the slide, and then we have to move on. There's also a USB-C thing. I wonder if that helps. Uh, yeah, there's a little switch here, I think. Okay, but let me try it. It's not going to record. You mean? Oh, this is working. Wait, allow, start mirroring. Ta-da. Uh, uh, damn, doesn't look like it. Try now. Sorry, folks. Yeah. Oh dear, what? Okay, so I want to show my entire screen and I want to start mirroring. Oh, but this is like somehow frozen now. Okay. Anyway, so you had the Earth tiled into a bunch of hexagons, and these hexagons were mainly meant for movement analysis. So what you would do is you would have very small hexagons across, let's say, a city, right? And you probably, well, God damn it. That is a very good idea. Yes. Right. And so you could say, okay, my taxi started here and moved here, right? And in this way, you were not limited by sort of north, south, east, west directions. You were not limited by the idea that a compass direction somewhere in Sweden might mean something relatively different to a compass direction somewhere in Brazil, for example, which is closer to the equator, right? Um, so this was one thing that sort of started this off, and then people started coming up with other grid formats. So again, sorry, this is going to be a little bit small. Oh, this is pointless. You can't see this at all. I'll put the slides up somewhere and you can see them. But so, for example, for climate simulation, right? Some people said, okay, we're solving PDEs, right? So we want squares, but we don't want one square for the whole globe. So let's just take a sphere and project it onto a cube, right? And so you took the sphere and you literally projected it out onto this cube. So you got 6 faces, right? Which were each their own sort of projection. And that's what got called a cubed sphere. So that gets used a lot in atmosphere simulation. NASA uses it for some of the satellite outputs and simulations, for instance. Um, and then the ocean guys said, no, no, wait. You know, I care a lot about the oceans. I don't care about Antarctica. And I care a lot about the area in the Arctic near the North Pole because that's also an ocean. So I'm just going to take a sphere, and instead of having one pole of my grid, I'm going to have 2 poles, which are over land. Sorry, this might be a little small, but I hope you can sort of get the idea here. Um, and so there's a lot of these different kinds of grids which were meant for different use cases, right? Which were meant for people to try different things, which had data layouts that were good for specific applications. Um, and so a lot of these things can be called discrete global grid systems, but I think for our purposes here, we're going to focus on more of on some of the more standard ones. So, tripolar grid, nice for simulation. I don't know if I really want to put data on this thing, right? So, so a lot of global grids are meant to fulfill some criteria. So, for example, Uber's was meant to be very regular to facilitate movement analysis. Alex over here made another grid called IGO7, which was meant to be hexagonal, but each cell would have sort of equal area, which H3 didn't fulfill. If any of you have experience in astronomy, you'll probably have heard of HELPIX, which is a discretization of the globe again on 12 different faces. Um, and so many of these grids were meant to be hierarchical. So for an example, let's say I have, just to define hierarchy, let's say I have a large square here. I can chop this square up into four pieces. I have 5 minutes left total. Oh, okay, cool. I can chop the square up into four pieces, and I can chop this up again and again and again. And eventually, so this is what we call a quad tree, right? So it's just you have layer one, which is the large square, layer two is which is the four small squares, and then so on and so forth. You keep subdividing and subdividing and increasing the resolution of each cell. So a lot of DGGSs also have this kind of hierarchy, which makes it quite nice to descend into them because you can, you know, suppose I have a polygon here and I want to check which of these cells reside inside this polygon. If I know that this top level cell is completely inside the polygon, then I know that all of its children will also be inside the polygon, right? Because it covers all of its children. So this is on the plane, of course, but you can imagine a similar thing on the sphere, right? Hexagon composed of, I think it's what, 7 different hexagons inside it. Um, yeah, unfortunately, I had cool graphics, but not not really very visible. Um, so other things you can do with DGGS is, so what do you do with these things once you have them? Well, one thing you can do is just the standard sort of zonal analysis that you would do with a raster. So let's say I want to know the average rainfall over Chile for the month of June, right? Which might be very low, but what you can do is you can go and say, you can take some data which might be available in longitude latitude, which might be discrete satellite images, which might be any sort of thing. And you can regrid that onto um, any DGGS you want. In Julia, we have some tools for that, which are sort of maturing. And then you can say, okay, give me all of the cells in this grid or this grid, which lie within this polygon of Chile, which is on the sphere, and then just sort of average the values in those. So that might get you a better number. That might get you, uh, in some cases, even well, you could be relatively as fast as rasterization for some cases. It's always going to be a little bit slower because it's more complex. But yeah, so that's one use case. Another use case which is interesting is stencil operations, right? So when you think of hexagons, you have this neighborhood which is well defined, and you can sort of you could do a convolution, you could do machine learning on these. Um, Another thing that you can do is, of course, yeah. So again, zonal statistics, but on data which is less than of a smaller size than the whole Earth. Okay. Any questions? Yes. Up top. Yes. Yeah. Yeah. Yes. What I'll do is there's a Slack channel called #Geo on the Julia language Slack. And I'll put some links up there. Also, if other folks here want to send me links, I'll just put up like an aggregate of links to all of these posts. uh, yeah, those would have looked fun, but oh well. All right.
it's working? Yeah. I think the USB-C works. The HDMI, for some reason, does not seem to be working. I mean, anyone watching online, I think, means won't get to see my slides. But at least people in the audience. Don't.
Just to show the slides. But yeah, okay, so I'd like to introduce Simon X, a package called mathmaths.jpg, which does, I think, sort of a bunch of different projections in pure Julia. So take it away.
Thanks. Uh, yeah. I'm Simon. I'm here to talk about mathmath.jl, flexible and fast Julia package for flexible and fast coordinate transformations. So just to avoid any confusion, what I mean by coordinate transformation, I mean things like taking latitude, longitude, altitude triplet, converting it to Cartesian, things like that, the kind of stuff you need for geospatial computing, for drawing maps, these sort of things. Okay, some of you might know Julia already has two packages which do exactly this, namely geodesy.jl and coregraph-systems.jl. So you may be thinking, do we really need yet another package doing the exact same thing? And obviously my answer is yes, I think we do need one. And the reason for that is that I think these existing packages, they are still incomplete. For example, one respect in which they are incomplete is that they are missing conversion methods. For example, in coregraph systems, I can happily convert from latitude, longitude, altitude to Cartesian and from Cartesian to spherical. But if I ask the package to convert from latitude, longitude, altitude to spherical, it says it doesn't know how to do that, which is funny because clearly it knows how to do that. It just doesn't know that it knows how to do that. Gripe number two is the existing packages, they are missing types. So for example, geodesy has no UTM type without altitude, while coregraph systems has no UTM type with altitude. I think both of these types, they have the use cases, and it would be nice if I as a user could choose whether I want an altitude or not the package making that choice for me. So I hope I managed to make a point that like, okay, these packages maybe could still be improved. But now you may be wondering, well, wouldn't it be more productive to just write up the missing methods and the missing types and then peer them into one of the packages? That way we don't have to reinvent the wheel. Well, I think this approach is not going to scale. And the problem is that in coordinate transformations, you want every coordinate system to be convertible to any other coordinate system, which means the implementation of every coordinate system depends on every other, which means you change anything anywhere, you will have to make changes all over your code base in like random places, and leaving this up to humans to manage this sort of complexity will inevitably lead to the sort of omissions and inconsistencies that I've just shown. So that was the motivation behind mathmath.jl. The idea is take the human out of the loop as much as possible, put just as much work as possible onto the compiler. Use the compiler to generate conversion methods for you. How can we do this? Well, the first idea on which mathmath.jl is based is this idea of a conversion tree. The point is take all the coordinate systems you want to support, arrange them in a tree, and then tell the compiler, if the user asks for conversion between any one of these types to any other, then just follow along the edges of this tree. Obviously, what this buys us, now I no longer have to manually implement every pair of coordinate transformations. Now I just have to define the edges of this tree, and the rest can be filled in by the compiler. The second idea is what I started calling atomic conversion rules. So the idea is you want humans to focus on implementing like the very basic, most concise version of every coordinate transformation. And then you want to use the compiler to synthesize composite coordinate transformations out of these atoms. So for example, you want humans to implement the conversion from just latitude to the Mercator Y component and from just longitude to the Mercator X component. And then you want to leave it up to the compiler to synthesize the conversion from latitude-longitude pair to the pair of Mercator coordinates, do that for you. What does this look like in practice? Well, here's the complete implementation of the web Mercator coordinate systems in mathmath.jl. As you can see, it's just 13 lines, split into 3 blocks. The first block is type definition. I define a type for the x component, the y component, then a web Mercator type, which is the combination of x and y, and the web Mercator altitude type, which is the combination of x, y, and an altitude component. The altitude component is taken from elsewhere. That's basically can be reused from your latitude longitude type, because there you also have an altitude that works in exactly the same way. The second block defines the conversion tree. Effectively, what this is saying is if you encounter anything web Mercator related, then convert to latitude longitude first, and then proceed from there on. And finally, the last block is just the explicit conversion rules from longitude to web Mercator x, from web Mercator x to longitude, and likewise for the latitude side of things. What does this give us? Well, first of all, now we can convert from web Mercator x to longitude. Not very surprising. That's exactly one of the conversion rules I just defined on the previous slide. But as mentioned, the compiler can synthesize composite conversion rules out of this for us. So for example, now I can also convert from web Mercator to a pair of longitude latitude. And the big advantage of leaving it up to the compiler to generate these conversion rules is that now we can have a lot more flexibility. For example, if you're the kind of person who prefers latitude longitude order or longitude latitude order, well, the compiler understands now what you mean if you just swap the arguments, and it can generate the code for you. Next up, we can also add an altitude to our Mercator coordinates and convert the result to Cartesian. This method here is noteworthy because the implementation of Cartesian doesn't know anything about web Mercator coordinates, and the implementation of web Mercator doesn't know anything about Cartesian coordinates. But by the power of the conversion tree, this conversion still just works, because the compiler now knows if I want to convert between these two, I have to do a step via latitude longitude and then proceed from there on. And finally, I can also do slightly wonky things like take a web Mercator y, add an altitude to it, and compute just that Z component of the Cartesian. Um, this is something you would never want to support in geodesy or quarter F systems, because if you start supporting these sort of operations by hand, you will go crazy writing out all the possible conversion methods. While here, because most things are compiler generated, well, the compiler can just generate this for us if we need it. Okay, finally, a quick note on performance. Well, Julia is really good at optimization. So the long and the short of it is, for the most part, uh, the code that is generated by MapMath is as fast as your handwritten code. So the concrete example I picked out here is conversion from web Mercator altitude to Cartesian. You see MapMath.jl takes 47 nanoseconds, Quarter Systems also takes 47 nanoseconds. Geodesy takes 51 nanoseconds, so slightly slower. Yeah, and that was my very quick introduction to MapMath.jl. Please give it a try, and I hope you find it useful. And I think I should have some time for questions. Yes. Yes. So I'm guessing you're referring to. Okay, so there's two macros here. This one here is a macro I've generated specifically for this package, but technically this is generic. This macro just takes a function definition, uh, looks at all the arguments, and then generates for you all the permutations of the arguments, which works because every argument is explicitly typed. So every permutation of the arguments is a new method, and it just writes out all the methods for you. The other one is a simple vector coordinate system. Yeah. Well, I mean, technically that one we don't even need, because what is actually we have a type, we have a composite coordinate type, and this here is just a convenience method which gives a name to the composite coordinate type and pretty prints it. That's the only thing it does. But technically, from just a functionality point of view, we wouldn't even really need that one. Okay. Uh, I mean, my main focus so far was to just get the framework ready. And the idea is once the framework is ready, then everyone can jump in and contribute to implementations. Because from now on, right, like you can work on whichever coordinate system you work on, someone else can work on what other coordinate system they want to work on. As long as they both attach to the same tree, everything will just compose, which is something that is not the case for the current systems. For your specific question, I think so. Uh, I do have spherical, and I do have the geocentric London delta, and I have the geodetic. I don't have othalic. But yeah, I mean, it's a question of exactly copying over the code. Yes, I mean, it's purely functional. So as you can see from the benchmarking macros, there's no allocations here. And in fact, if I hadn't done this funny thing here of like creating the object first and then sticking it into the function that I actually benchmark, if I just benchmark the expression with everything filled in, it would actually constant propagate. So yeah. I think it would be. So currently I don't have something like that, but I think from like a design point of view, what is related is local coordinate systems, which are also, I mean, they're related in the sense that you have something that's like not a static type or something you want to inject at runtime. So in local coordinates, right, you have your origin, that you don't want to make it part of the time system, you want to pass it around as part of the coordinate system. And this is one aspect in which I differ from CoreDrive systems. CoreDrive systems, they usually stick everything into type parameters. In Julia, the coordinate systems, they are types, and they are first-class objects themselves. So you see WMX, that's a coordinate system, but in Julia language, it's just a plain type. And if I want this to depend on something, I can just stick in parameters and then use that parameter in the implementation down here. Course, yeah, so I guess that's like the difference between webmercator and webmercator alt. Am I understanding this correctly? Or okay, like a geodetic and a geocentric. Yes, so that works. And in fact, I chasing purity, I did implement geodetic altitude, which is like uh, which okay, let me draw a really, so I have a geodetic altitude which is this distance, and I have a geocentric altitude which is this distance, but so you can support different things.
So for our next speaker, I'd like to introduce Daniel Luz, who will be talking about his package dggs.jl, which is an implementation of, I think it's just one global grid system at the moment, right? Cool. Alrighty. Yeah, I think this HDMI thing is not working, so
It used to work a couple of minutes ago.
yeah, let's. Well, so this was the thing that was working was the USB-C. Oh,
No.
oh, yes. Okay. Awesome. It's just enough. I know. Okay, let me restart it before the next one.
All right. So I want to introduce the Julia package ddgs.jl, which is about global discrete global grid systems. So when it comes to projections, we already learned that the Earth is indeed not flat. So when it comes to project those, there is a trade-off to be made. Projections can be either preserving area or shape. So this is an issue we need to fix in general. And a common solution for this is to just use multiple local projections. This idea has been around since World War II. And here, for instance, you see the UTM grid, which is used in Sentinel missions and others. So there's some drawbacks to these methods because if you have tiles and the local zones, those tiles might overlap. We need to deal with this. And we also need to keep track of which current UTM zone we are. And when it comes to global grid systems, we want to think globally, and then we don't want to mess up with all of those zones. And due to this overlaps, of course, maybe we might need to store more data or allocate more data in memory. Another solution is based on grids using polyhedrons. They have been quite extensively being used in weather simulations, including the icon grid from the German Weather Service, or the one from ECMWF or Google GraphCast. So discrete global grid systems is yet another solution to this issue, trying to provide you a seamless tessellation of the globe's surface. The projections, as we already learned, are based on the faces on the polyhedron. And you not only have a grid, but a system of grid at different spatial refinement levels. It's not a idea. It has been standardized by ISO and the Open Geospatial Consortium. And we already mentioned that Uber A3, but also Google also introduced some of those systems. The thing with district global grid systems, however, is that they are not equal. There are multiple methods, and some of them yields to cells in which their area is not exactly the same all across the globe. And sometimes the individual cells are not always homogeneously distributed. For instance, we learned that even if you want to use hexagons only, you need to introduce these 12 pentagons, and sometimes the polygons of the cells are not always the same. So this is why we opted to use district grid systems based on the Snyder equal area projection. So that's Mainz. That's where we are right here. That's data produced by DGGS JL. And this is just to introduce the aim of this project, which is to create low distorted DGGS raster arrays on disk at high resolution. Introducing DGGS JL, the Julia package to create and visualize DGGS native data cubes. It's available on GitHub, and pull requests are, of course, always welcome. So if you have points or polygons on the spherical surface and you apply this ICEA projection, currently we're using bindings from Proj because it's a well-tested code base. You're ending up with those 5 little rectangles. And if you skew and rotate them, you are basically ending up with coordinate system pretty neatly arranging into rows and columns. And this is how we store our data. So you start with your TIFF files, maybe originated from a stack catalog, and DDGS.jl will turn it into a SAR store in DDGS format, and then you can use it to access the data cube, either using Julia packages like YAX arrays or even other tools. So I talked about grid system. We have different spatial refinement levels, and each of those 5 big matrices covering the globe have lengths in power of 2 elements, meaning that we can just create the next subsequent resolution by merging 4 pixels into 1 or 4 cells in DGS terminology. So this is the blue marble dataset at resolution 10, for instance, resolution 8, 6, 4, and 2. Those plots were generated using Markey. So we provided a plot function inside DGGS JL where you can plot either individual bands or just one band, and then you have the color scheme. Beside that, we developed DGS Explorer, which is a web server based on Oxygen JL, providing you XYZ tiles using this DGS-JL package. So you can also browse your data cube in the browser. Because we have XYZ tiles, you can also view those data cubes in other applications, including QGIS. And for instance, if you zoom in near the coastline of Gothenburg, Sweden, here you can see that there's a corner of the polyhedron, and we have cells pointing towards this, indicating that indeed here we are dealing with a DGGS dataset. As a first result, we created a DGGS data cube of Germany using 96 tiles of the Sentinel-2 mission. And this is basically the zoomed out version of the Mainz view I showed you a couple of seconds ago. This is how it looks like in the Julia REPL. So you can open a pyramid giving you all of the different spatial resolutions. And this data type, this struct, is based on dimensional data. So the DGGS pyramid is subtyping the abstract dim tree. And we just added a few more metadata information, like which DGGS reference systems to be used. For now, there's just ICA 4D, but of course, in the future, we can add other systems as well. And there's also the bounding box in geographical coordinates to be stored, which is quite handy to have an overview plot. So a data set basically is just a pyramid at a given spatial resolution. And here we have one more metadata field giving us the current resolution. So this is a abstract dim stack. An array is just a tensor where we have the same element type, which is part of the collection of arrays at the same spatial resolution, which is the data set. So here, basically, the metadata is the same as in the data set. And that's an abstract dim array. At the end, a DGS array basically is yet another YAX array. So we can produce a YAX array based on the DGS array. And the only thing that is special here is that we have a couple of metadata fields being added prefixed with DGS. Of course, this is not a Python exclusive thing. It's just a SAR array. And if you're curious, this is how it looks like in Python on a Jupyter notebook. Thank you. Yeah, so basically you can read any ZAR store in Python like this, but this doesn't provide you plotting. So you can plot individual tiles in DGS format. Um, for instance, this is how I did it here. So these are the plots you currently can do in any language, but of course it would be also really helpful to have Python native implementations for all of this plottings. This is basically also the motivation I created the web server, so at least we have the XYZ tile server to include people from other languages. Alex? Yeah. Yes. Indeed. So basically, there's different coordinate systems even for the same DGS reference system. And since I focus on arrays, I use array and axial coordinates. Of course, I mean, in theory, we can add other coordinate systems as well. But I think it's a really good thing that Pangeo started with like trying to standardize all of the different formats. And this is really important. So not only Julia people making their own standards. I think in the future, we definitely need a more common standard. So right now we're using Proj just to get to the XY plane. What is done in Julia right now is this rotation and skewing to get the integer indices. Of course, it would be better to have the ICEA projection itself being implemented in Julia, but I'm just focusing on arrays and trying to make a data cube of Europe, and this is why I'm currently still using the Proj code base. All right, I think we are finished with the time.
We still have time.
Ah, okay, maybe one last one. Otherwise, I'd Felix. Yes, for the first time. This is also like one thought I had 10 minutes ago. If we have this icosahedral Snyder equal area projection in the new Julia package already, it would be a breeze to just use it in other Julia packages. And I think this is also the reason why we have the Julia implementation. But there's so many different projections, and I have the feeling that, okay, everyone is just using Proj. So maybe it would be too much effort just for me to re-implement everything.
While Simon is setting up, I just wanted to say something. I think we have two stations and I see a projection. Rather, we Right, so our next talk is from Simon Lupemba. He is a member of the UMedSat Institute, or I don't know what the thing is, but organization. And yeah, he works on, I think, the MedOps satellites, which do a lot of like wind monitoring and that sort of stuff. So yeah, great to have you here.
Thank you. So I'll be presenting about meta datasets.jl. I'm unfortunately, let's see if this works instead. I allow and I extend stuff. Yeah, okay, perfect. Then you also get it with the slides. So meta datasets.jl. Yeah, so the content of the presentation, first I will touch a little bit about what is MetUp, because otherwise this package doesn't make any sense. Uh, then the MetUp data formats, followed by a little bit about the package, and then I will try to say something general about how to interface with domain-specific formats and what we can do to make it more accessible. So first, METUP is a series of satellites, and they are part of the EUMETSAT polar system, EPS. EUMETSAT is the European Organization for Meteorological Satellites. It consists of there's three almost identical satellites in low Earth orbit. The first is METUP A, which was launched in 2006 and retired in 2021. And there's two satellites still operational. Uh, each satellite carries a range of meteorological instruments, and they have near global coverage. And these observation is a key ingredients in numerical weather predictions. So there's a good chance that if you looked at any weather forecast for the last 2 decades, it contained data from these satellites. The data is widely shared, and it can also be found at the EUMETSAT data store if you Google that. So the data formats. The data formats are a domain-specific binary format, which can be kind of tricky to work with. It consists of a main product header, which is in ASCII and is standard for all the different product types from all the different instruments from the METOP satellites. But the actual data are stored in data records, binary data records, and these have different binary formats for the different products and the different instruments. So there's this documentation you can look up where you can find this nice table which gives the binary layout of the different products. Yeah, but it's not even that simple, because not only does each product have a different binary format, there's sometimes, because the satellite have been operating for 2 decades now, there have also been different versions of these formats. So sometimes when you go to historic data, you find one version, newer data change slightly. Yeah, and there have been some tools to read this, but a lot of them were made around the launch of the first satellite. There's coming a new generation of tools now, but yeah, it's uh, it's been a bit of a mix status. So I started to make MetUp datasets, and it started as an internal tool just to read this data easier and to better interface with it. Now it's a registered package. It supports 7 out of 10 product formats. So there's still like a few products from the satellites it's not worked for, but I hope to get it finished soon. Um, it's read only. I don't think it was ever intended for anyone outside EUMETSAT to write these type of formats. It's a way for EUMETSAT to distribute the data. Um, yeah, and the way I commonly use this packet is either to just open the dataset and directly carry out analysis with this package, or for larger datasets, I actually often use it to filter and extract the variables I'm interested in, because there can be like a lot of variables mixed together and different spectral bands. And then I store it in a data frame or a data cube, and then that can be used for machine learning. Um, yeah, personally, I don't really use it directly for big data analysis. Yeah. So what is it? It's a packet to reach the data, and it uses a common data model, the JL interface. So it provides a interface quite similar to NC datasets.jl, which means that you can kind of open and work with these files as if they were NetCDF. We're kind of using the same interface, and therefore we get some a familiar interface. The binary layouts data types I automatically construct from the data record tables. So the binary tables, and then uh, the record type is automatically detected from the main product header. So I try to give this one function to open all the the different products, so you don't have to know which product the specific is to call a specific reader. And there's a lot of scaffolding in there to handle like these different caveats and things that are with the different products. It enables some easy conversion, so it's easy to change back and for to convert, for example, to NetCDF or more common formats. Just a little bit about what's in there. So MedUp dataset has like a range of instruments. There's passive instrument in from microwave to UV, so there's a lot of all observing the Earth, and then there's also a scatterometer. Um, I just took a plot from the documentation to show you an example of one um, one observation from YASI, which is the infrared hyperspectral sounder, and it measures the brightness temperature in yeah, almost 3,000 different wavelengths. So really giving a full spectrum of the atmosphere. And then it's used to also retrieve humidity profiles, temperature profiles, ozone, all these kind of things. Yeah. So on a more general note, um, interfacing with domain-specific languages. So this I use common data models here because it provides a nice interface. I think the abstraction layer really can lower the barrier to entry. Um, Earth science has many domain-specific formats, so I think it works to consider if we can do something similar for other domain-specific formats to make them more accessible and to make them accessible outside the domain. Of course, there's some pros and cons. I think for me, the pros have clearly been that it's like lower the barrier to entry. It makes it more compatible with other packages to use, like a standard interface, productivity, easy conversion. And I will also say it doesn't, just because this interface and this reader exists, it doesn't exclude other more performant readers from also coexisting. I mean, it doesn't have to be one on another. The cons is there is some performance penalties. The abstraction can often hide the true data layout, so the way that you see the data it's presented when you open it is quite different from how it's actually stored on disk. And that can of course lead to some performance penalty, and also like matching the format with the interface is not always straightforward. So in my case, I needed to do some padding to have some variables a common size because there was some compression going on in the format. I needed to have some groups because there were different subtypes, and then also one thing that was needed was some type conversions because the data formats contained quite a lot of custom types. So converting these to, I automatically convert these to normal Julia date times, or I convert these to floating point values to give like a better user, a easier user experience. But again, I mean, I hide the actual type that the data is. Yeah. All right. We have some time for questions. Thank you. Oh. Yeah. Yeah. So I mean, I actually described the chunking in some way with disk arrays. So this data record often consists to, for example, here it's a group of these observations are taken in groups of 4, and then it's stored in one scan line at the time, which consists of one data record. And I actually include that in the chunking in disk arrays, so it is aware of it when I read it that it's chunked this way. But yeah, and there's also other places where it comes in. But again, when you just look at it as a user, because the way that that the interface is, it's the interface divides things per variable. So you get a tendency to, instead of I mean, it's a bit going back to how is it, array of structs or structs of arrays, and the common data model in generally look more like a struct of arrays, where the true data format is actually more a array of structs. Any more question? Yeah, I mean, I think the units could be used more. So, I mean, I don't know. So what I did was I didn't do the units so precise. There are some units listed in some of these table format data description. So I just pulled the units from this table, and then I put it as the unit that is shown in the common data model as like a unit attribute. But there's no guarantee that there's no typo, or it matches an actual SI unit. And the places where the unit is not, I of course just replaced it with nothing. But I just, as a first iteration, just took it from the table to start with. But yeah, it's good to have units. It is in the metadata, but it's not like how you say. There's not the unitful uh, abstraction on top where it actually enforces the units. And
So, I think our season's on 15 minutes again. 11:15 will start right here.
Okay. You don't need
All right, so let's start again. Welcome back from the coffee break. I'd like to introduce Dr. Fabian Gans, who is at the Max Planck Institute in Jena and is going to be presenting his package called Spherical Spatial Trees, which deals with interpolating from very large rasters on the cloud or lazy rasters to very large DGGSs.
Yeah, thank you, Anshul, and welcome to my presentation on the Julia package spherical spatial trees.jl. In principle, this package was more or less built around a quick idea that I had that has to do with bounding boxes but first let's look at the main problem area, and that's when you want to reproject tiled large arrays. So for example, assume you have two different projections. So we have an original data set here in longitude latitude, and they are tiled like this. These are the chunks of your data set, and we want to reproject it to IC, for example. And then the question is, when I want to compute the values in this quadrangle here, the question is which chunks from the source data set do I need to access? And here that's really easy to determine. I mean, like you see, okay, I probably need to load these 4 chunks or access these 4 tiles or whatever to compute the values inside this IC. And of course, this also applies to when you go higher resolution. I mean, like when you want to go really to high resolution shell data, then your tiles get smaller and smaller. So they can also become like this. And then this lookup task, I'm like, when I want to determine, I have a certain IC tile in here, and I want to determine which rectangles do I need to access to reproject into that. This really can become slow really fast if you do it the simple way. I mean, like if you just do an intersect between all the combinations, but this really grows quadratically in time. So what you really do here is you use some spatial tree data structures to look up which tiles do I need to reproject from here to there. Okay. So, and whenever we do spatial trees for polygons, we need bounding boxes. And the very common approach is to do axis-aligned rectangles around our polygon. So here I have just an example polygon, and when I compute the extrema of the x and the y dimensions, I have a bounding box, and that's very cheap to construct, and it's also very cheap to test if some point is inside or outside the bounding box. And in addition, the rectangle is convex, so whenever I know that all my points of the polygon are inside the bounding box, also the lines will be inside. So, however, whenever I reproject the bounding box, now we want to reproject and we want to do this test, which tiles do I need to access to go from one projection to the other, then the bounding boxes change their shape. And when you interpolate and reproject, then you see that it's even worse. The bounding boxes are also not convex anymore. So what can happen and what also really happens in real situations when you do this lookup and you just reproject bounding boxes is that sometimes you miss a few input polygons and you have some white stripes when you do this reprojection. And so the simple idea that the whole package focuses around is that instead of using these rectangles as bounding boxes, we just use circles on the unit sphere. And the nice thing is that these circles project into almost all projections, and they are still convex after reprojecting. So you see here that the reprojected polygon is always inside the circle. So you don't need to do these additional checks and polygon interpolation and so on to find out if really all your polygon is inside the bounding box. And then we basically, I said, okay, let's try this. Let's really try to build a package that does reprojection, or that does this lookup of which tiles do I need to reproject from here to there. That does this lookup through these spherical spatial trees. So I extended the the spatial tree interface from geometry ops that was done by Anshul to produce spherical bounding boxes, like that uses spherical caps as bounding boxes. And yeah, and I implemented different grids. And what you can also say is that many grids, as Anshul already showed here, I don't know where it was. I mean, they are basically quad trees also by nature. So what I'm doing here, I make to do these lookups. I basically implemented very simple quad tree implementations for these different grids. And the most simple one is this what I call regular grid tree, which is just a longitude latitude grid that gets split and split. And here you see basically for every of these bounding boxes, you see the circle drawn around it. And yeah, and then you can get to higher resolutions. And whenever you do this search, you always just check if a certain point is contained in a circle or if the circle is touched by a certain tile. And then you descend into the tree again and you get an efficient lookup of which tiles you need. So the next one that is implemented in the package is one that uses IC projection. So here the tree is three-dimensional. You have the number of tiles. I use 10 tiles here, not 5 as Daniel does, because you get nicer circles around the smaller diamonds. And yeah, and then it looks like this. So here I have my 10 diamonds, and you have the enclosing circles. And because it's a bit complicated, the plot, we concentrate on this one diamond. And then in the end, okay, you don't see it in this projection, but this is actually also a rectangle. I mean, the North Pole is just a single point. And then you can again build a quad tree by separating this diamond into again 4 sub rectangles and so on and so on. And we go to higher resolutions. Yeah. So this is the next level of recursion. Yeah, the UTM projection, that's also a bit difficult because here in the end, when we have data in these different UTM zones, we have different projections for all the different zones, and we still need to make some tree that can efficiently index into these. But in the end, it's possible. It again looks a bit strange because these zones are projections are overlapping, so you get overlapping polygons. But if we concentrate on a single one, you again see, okay, here in the end, this is just a subset of some UTM bounds, and we can again draw circles around them, and then again split them into 4s. We have an Equi7 tree. This is the thing that comes actually really closest to a real spatial tree because it's not just a quad tree, because we in the end have all these Equi7 tiles. I mean, okay, here you don't even see them because the line width is too thick. And we have all these Equi7 tiles. And then we basically do a real tree split until we are inside just a single tile. And then we are inside a tile, then it's just a normal quad tree again. And then we basically go to the normal tree. But as I said, I mean, it's also a nice lookup. Yeah. So like this, yeah, I make this is then again just one subset of Equi7 Europe tiles. Yeah, we also did red Mercator, but that's again just a rectangular tree. So to summarize, I mean, we have many projections and grids implemented. I mean, to have these efficient spatial tree queries into a common interface. And we don't need to deal with polygon interpolations. We don't need to special handle the Dane boundary and so on. It just works. Can I take one more minute to show that example? And so to just see that work, I mean, like here, I just have one abstraction. This is the Alpha Earth embeddings from Google, just loaded as a single array. And it's basically just thousands of UTM tiles. I mean, just the index catalog is 70 megabytes that you can download, and you have many tiles. And we just arrange that into like lazily into one big abstraction of a huge YAX array that has like the number of the index of the embedding, then the XY coordinates in UTM, then which UTM zone we are in, the hemisphere we are on, and we have different years. And yeah, you can just query the index that's closest to the city of Jena. And then we just plot a box that has 200 by 200, like 2 by 2 kilometers around Jena. You see the river flowing through it, the stadium, and so on. And then let's say we want to lazily reproject that to the web Mercator projection. We just make this tree a projection source. We define a projection target, which is the web Mercator at a certain resolution. And then we can make this lazy projected disk array. And reading data from that and reprojecting a small box that is like, again, 400 by 400 points is done in way less than a second. So this look up which tile do I need to access, loading the data, plus reprojecting it is really almost instantaneous. Yeah. So, and then when we've reprojected this thing to Web Mercator, of course, we can plot it together with some data that's also in Web Mercator. So we just, I just made a small abstraction that takes any tile provider and makes that a Yax array in Web Mercator at a certain zoom level. And then we can plot the one band of the alpha Earth embeddings together, like the reprojected to Web Mercator together with the actual image. And yeah, so and here I would like to stop. Thanks. Daniel. Currently still a lot. I mean, so like adding another tree is still quite some manual work and thinking about how to do the splits and so on. I would really like to, I mean, the more you implement, the more abstractions you generate. I mean, like, of course, I did not start like map maths. I mean, like, so from the abstraction and then, okay, let's first build a tree, how all these connect together. And let's make something, but yes, currently it's still manual work. Yes. Yeah. Alex? Yeah. Yes. Yes, yes. I mean, like, I assume that we want to transform data from grids into grids. Yes. I mean, that's still the assumption, although it doesn't need to be. I mean, like, in particular, this special tree interface, I mean, you can use it to query anything, but I would argue that whenever you really are dealing with high resolution data, like you go to the 10-meter resolution, there's no way to use traditional trees because like you cannot put all these 10-meter polygons on a global scale into a single instantiated tree. I mean, like, so you must use these type of theoretic, hypothetical trees. I mean, like that come from the definition of a grid. Yeah. Yes, let's discuss this. Yes. 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 So currently, I make the thing I implemented is just a nearest neighbor projection, but I need to say, I make actually what I think this package is about is really this look up which tiles do I need for the reprojection and have the right data in place at the right time. There is basically the actual reprojection is just a small script that's more or less factored out. So I mean, like we could use some conservative regridding in the end to do the actual reprojection. I make so most of the package is just about loading the data. Yeah. And of course it's, yeah, I don't think it will be a standalone regridding package. It needs to be integrated into something else. Yeah. Yeah. Yes, 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 definitely. Yeah, that's not the end of the story. Yeah.
All right. Yeah. Looking good. Thank you very much. Okay. Hi, I'm Alex. I'm associate professor in the University of Tartu in Estonia. I want to tell a few things around how I use DGS together with spatial machine learning for soil properties modeling, basically digital soil mapping. So I have a lot of different concepts here. I hope I can try to convey them in a way that they still make sense together. So our team, we are based in Tartu. We are the landscape geoinformatics team. We're really keen on open source. So we also, QGIS, a sustaining member, OGC member. We organize the Phosphor-G. So if you are geospatial folks, you might have heard of the Phosphor-G. And then our research is mostly around land-based application, water quality, soil, land use. So in this sort of context, we had the DGS introductions now a couple of times. So, of course, traditional spatial data challenges, those ones that Fabian also tried to solve, regarding resampling, reprojecting. What if we wouldn't have to do that and we just live in one grid? And that would be, for example, a DGS. So, of course, as they become more popular, we've seen now, if you would have seen in Anshul's presentation, there's already several ones, and they all have different advantages and disadvantages. So this global grid system is a spatial reference system that can hierarchically tessellate and partition and address the globe. And I think the addressing bit becomes very interesting in regards also what we've seen already before. What can you do with the DGS? You can do binning, you can do spatial indexing, or we can do data cube, where we treat each cell as a pixel, in an analogy to a raster, right? And so I'm in the data cube camp, and my preference is for hexagonal DGS, because in the landscape where we do most of our research, we have equal neighbors. So one of the nice things is that we don't have to deal with like 4 versus 8 neighbors, like in classical landscape modeling, but we always then have the same neighbors. This is great for hydrology, geomorphology, etc. One of the very, very popular hexagonal DGS systems that you might have come across is Uber's H3. I did a study a few years ago where I sort of starting to get into this whole, and it uses a projection, the mnemonic projection, and that makes the shapes really nice, but it has introduced area distortions. So within 1,000 kilometers, the cells would already be like 50% larger or smaller. So that's not so good if we want to do spatial modeling when we introduce statistical biases, because our pixels are now very different size. That's why I worked with the author of DigiGrid, Kevin Saar. We came up with an ICR projection using, which is equal area, 7H, so the same 7 children to one parent tessellation that H3 uses. And we added a really cool indexing system. And the indexing system is maybe a little bit sort of hard to understand. I can give a whole talk only on that. But the idea is each cell has a unique index, and that is through a space filling curve, and that is represented as a 64-bit integer. And we can reduce it to like a monotonic index. So we can say ranges from to, and this way we can actually explain whole areas as a small number of from to pairs. So this will this covers sort of a different approach how Daniel approaches to indexing and storing raster or pixelated DGGS data. But I want to do a spatial machine learning. So in our lab, we do a lot of research on water quality or soil, and we use spatial terrain, satellite data, etc., for variates where we have a full coverage, and then we have our sampling data, our soil data, and then we train a random forest, rather a simple model, an explainable AI model, and then we can use different spatial things to introduce into the model to make the model spatially more aware. So there's a whole research team going on. You can, of course, be very naive, use let long, but you can also use neighborhoods. Then you have to deal with cross-validation. You don't want to do a full random cross-validation. So there's a whole field behind it. And I want to combine this together with DDGS. So at first, I'm looking a little bit at our sampling data over Estonia. This is in the north of Europe. We have roughly 1,000 sampling points. We look a little bit at the spatial lag, autocorrelation. So we see that within a few thousand meters, you have pretty high autocorrelation, which is to be expected in the landscape, maybe on a regional level. And the classic Estonian landscape soil map was in vector data, so we rasterized, but the next level is, of course, doing this in DDGS. So this is just a paper before, based on which this sort of experiment with DGGS and modeling now is sort of based on. And we arrive at R squared around 0.6, which is not bad, but it's also not great. But it is explainable random forest. You get Shep plots, dependency plots, and so on. So this IGO7 discrete global grid system, because it wraps always around the whole globe, you have only discrete levels of resolution. You cannot choose 10 meter or 100 meter. You're sort of bound to what the DGGS offers you. So this is sort of the resolutions that DGS, the IGO7 offers in that range that we usually work. IGO7 goes until level 20, which is like 2 centimeters resolution precision. And we don't need areas over Estonia that are larger than several thousand square kilometers. So this is just sort of a general orientation. And the CLS, characteristic landscape, because it's hexagons, they're approaching a circle, and you can imagine this being the diagonal of the circle. So you have a bit of a feeling what the pixel size is in compared to raster. So, and what we do, so we aggregated the covariates, terrain indices, NDVI, and some other things, soil texture, at the different levels via zonal statistics, from very coarse to very high, to our basically native resolution. And what we then can do is also we can look at what would be the drivers at the different scales, right? You have regional scale, you have maybe catchment scale, hill scope scale, or on the field level, or basically pixel level. So we can assume, if you know a little bit of ecology, landscape ecology, that certain factors will have only effects at different scales, like the weather, the climate does not make a difference on 10-meter resolution, but at coarser resolution. But then the slope, which influences the soil organic carbon deposit, so that makes sense already at like 100 meters, for example. Now, so we basically aggregated those at the different levels. We looked a little bit random forest and SHAP, and to select the important drivers, and then use them together to build multi-level models that you have covariates at coarse scales and covariates at very high scales. Resampling vector and raster data into the grid. There's different methods: nearest neighbors, zonal statistics, or conservative regrid. This is sort of just a side scheme here. And then basic performance tests. So as you can see, going from, if we make a single model at a single resolution, the finer we get, the better resolution, the better performance we get, which is sort of to be expected. But now, can we make this better by combining the machine learning model at different scales? So we can predict already, this is hexagons, maybe not immediately visible, but no, it's just a picture, like, it's a raster or what the underlying data is not so important. And then in order to assess uncertainty, we calculate something called area of applicability or dissimilarity index, where for each pixel or for each cell, the Euclidean distance in feature space with the closest, most similar sampling data. So this way we can say how how representative is a prediction at this pixel, because is it known or not to be similar to what the training has been seen. So in the upper right, for example, this is like an open mine. Obviously, we don't need to sample there for soil organic carbon because it's basically not useful, but other areas are quite well understood. And then in the South Estonia, the landscape is just super diverse. You have undulating hills. And then so this shows that actually our sampling data has not fully captured the environmental diversity, basically. So, and then at the different levels, if we do a really high one with mixed resolutions, then we get it a little bit better. So that's sort of like a first experimental try. So this is great. So we increased the model performance from 0.38 to 0.66, which is a little bit of an improvement, but it's worth to investigate it a little bit more. And then in terms of discussion, so scale-wise, so that is so far interesting. So we improved a little bit the accuracy and also reliability of that, and with using multi-resolution and DGGS, as we've seen, it can be really helpful in dealing with the covariate data. And then, admittedly, I'm coming a bit from a Python background, so, and then this was whole then built in Julia. So I ran into a couple of things, and I'm still rather a bit of imposter syndrome. So, but once it eventually ran certain things, they were definitely faster than in Python. So this is something that is the satisfaction why I went on to actually do all of this. And I was hoping I came to Julia also with a bit of the promise of the scientific incorrectness and the speed of the libraries, because it's a very science-driven ecosystems. But I ran into a couple of things. But what worked really well was, for example, this orthogonal conversion, because DGSs are only defined on the sphere usually. So when we go to WGS84 to the ellipsoid, then we need to do a little bit conversion. That is super fast with the quad ref system and geometry ops. Then I ported some of my packages. The MGA ecosystem is okay. I don't know if you have more experience, if I should have tried something else. Yeah. And there's some, I think, maturity or feature parity things where I'm sort of not fully happy, but it's something we can sort of work on. Yeah, that's all. Thank you. I'm here also tomorrow and the day after tomorrow. Yeah. If it's large enough difference, I would just do zonal statistics. And yeah, so if you have a very fine raster here in the upper middle, a very fine raster, and you want to have coarser, you just do zonal statistics. Yeah, median. Yeah, median or mean. Yeah, I think we did, including range. So that's how we then got those additional statistical covariates, also like range and standard deviation, in order to represent what is in there. Yeah. Cool. Yeah. Yeah. So
Probably 1 minute or so for some more AV issues.
I'll do the USB-C.
USB. like to introduce Martin Frank. He's what's your job title? Research fellow, something? Sorry. He's at Deltares, which is a Dutch hydrological modeling institute, and he's also the author of a lot of Julia geospatial packages, including this one, which is geodataframes.jl for reading vector files into data frames.
Absolutely. I'm already on my
Yes.
headset. Hey, thanks for the intro. I'm Maarten Pronk. I'm a senior researcher at Deltares, and in well, 1 day a week, I'm also a PhD candidate at Delft University of Technology, both in the Netherlands. I'm really loud on this headset, by the way. Awesome. Okay. Um, so I'm here to present something almost planar, which feels like cursing in this room with all the spherical and DGDS stuff, namely the state of geodata frames. And geodata frames is a package I wrote to basically read and write geospatial vector formats, just so you can get it and then do something fun with it. So I made a release like 1 hour ago. It is online, but given my own issues with the package registry, I'm not sure if you can get it. If you really want to get it, you should try the setting, what is it, eager registry or something in your environment, otherwise it will not show up. And I will just try to demo this live of all the things that changed since version 3, roughly a year old or so. So, okay, go away. I cannot make it go away. Okay, I'm gonna kill this and hope for the best with a live demo. You know how that goes, right? So at least after the release of the package, you can still use it. So I think that's a win. Is this big enough for everyone, by the way? Also in the back? Cool. Okay, so first new feature requested by Alex Gardner because he was, oh, well, he's lazy, doesn't want to download anything. You can read a raw HTTPS URL and it will automatically rewrite it to the GDAL virtual file system. So it downloaded the GeoJSON and read it in. So it will download in the background. Simple feature. You can also do the forward thing that GDAL needs manually, but it's a bit obscure. And I'd say let's just make it work. So that's one new feature. Second one, and that's a big one since version 3. We basically had GeoInterface, which is this great thing to access any geometry in the Julia geospatial ecosystem. But what it didn't have, or not correctly had, was geometry operations, like intersections and such. The package itself had to implement it, but many packages are only an IO file format, so only GDAL actually implemented it. So we said that's stupid. Version 03 had that. In version 04, we basically use geometry ops for everything. So we imported and export that now. And you can see that if you use GeoInterface, you can request the intersection with this point with itself. And of course, the intersection of a point with itself is true. But if you would then convert that point to, let's say, just a vector of floats, which is also a point in the Julia ecosystem, then you get a terrible method error because ArchGDAL doesn't know how to do an intersection of its own point with something else from the ecosystem. So don't use GeoInterface for intersects. I re-exported geometry ops, just intersects works. And this natively tries to convert one or the other to something geometry ops can understand and intersect with it. What we also added, because we have many native packages in the Julia ecosystem now, there's GeoArrow, GeoParquet, GeoParquet using parquet2.gl, and with the DuckDB extension answering your question, I believe. There's GeoJSON, there's CSV, right? There's all these file format drivers in the Julia ecosystem, and we're exposing them now in geodata frames. So we can write this to Arrow, and this is using GDAL in the background. And we can read it in again. But if we do import GeoArrow, you actually see that you will get a, using GDAL for reading, import GeoArrow for a faster native driver. This was all inspired by work that Rafael Schouten did in rasters.gl. Just has to compile a bit, but there you go. And now you'll see that you got the same table, same everything, but the type of geometry is now a geo-arrow geometry. And of course, if you then would do the old method of geointerface intersects, it will do nothing, but geometrips will happily eat it up and do something with it. So that's another feature. Then we have metadata now, also on columns. And if you would set random metadata, so let's set a foo'n bar on geometry column, see that it worked. We can write that again, and we can read it. And then you'll see that the metadata that we set natively in Julia actually survived a round trip using GeoArrow. This only works with GeoArrow and GeoParquet at the moment. You can use GDAL for this, but GDAL only understands metadata on the whole data frame level. It doesn't know about columnar metadata. So it's still slightly limited, but this was very useful for my own research because all these scientific data sets from NASA, like Simon talked about this, all the metadata that you need, it's really nice if it actually survives your file operations. So another improvement. And the biggest, and thanks for Anshu for actually approving my PRs in Geometry Ops yesterday night, if we would download, let's say, polygon of Germany using Natural Earth dataset, if you would represent this in ArcGDAL, so you have a GDAL polygon, if you would then request geointerface area on it, it's wrong. Right? This is doing a planar operation on latitude, longitude formats. Because if you request the CRS of this thing, it's actually in EPSG 43.6, so WGS 84. So you need another, you need to correct area operation. And before, and in the Python ecosystem, this also goes wrong. They might warn you about that it's the wrong answer, but it's still the wrong answer. This is now a correct one if you use geometry ops. Correct-ish. See, and you can even do a reproject, also a new feature, directly also using geometry ops. You get a new CRS, and the area is roughly the same, which is, I mean, these are all approximations, right? Another new feature is if you write this to a geo package and you read it back, there's now an FID column. So that's the index from any database that GDAR reads, and it's also in there. Anyway, that's enough about new features. I'm already out of time, it seems. Oh, I didn't show you website actually. We made a new website. In the spirit of the whole Julia Geo ecosystem, this is now in Documenter VitaPress. Lazaro helped a lot with this, or I think I copied many things from you. Thanks for that. And there's now actual tutorials and guides. It's quite well fleshed out now. In that sense, I don't think, oh, how much time could I use? So this is what I talked about. Then for next versions that I am still thinking of, and we can discuss in the community meeting, is I want to have cloud optimization, so read cloud optimized file formats. And now everything is eager. So if you have a geodata frame, it eats everything into your computer. So if you have a very large GeoParquet data set on the internet, you basically will run into memory issues. So you want to do subsetting, but data frame cannot do really subsetting lazily. So I will need to introduce a known type and might help with maybe trimming in the future, but it's also moving away from data frames. So I'm not sure yet there. If you have any suggestions, please let me know. And beyond that, I want to look at topology together with all the DGS people here, which are a lot actually. Thanks for that. Because there needs to be interoperability between, let's say, geometry, meshes, DGSers, and rasters in between there. You should all be able to convert from one format to the other, and ideally back, and ideally lazily. And it would also be nice if the operations are actually correct. So about correctness, some people here from the Julia Geo ecosystem, we go to the SDSL workshop once a year, and that's together with the Python and R ecosystem, and also the Rust ecosystem, I believe. And we talk about correctness, or at least some people want to talk about correctness. Basically, that if you call area on any geometry, whatever the CRS, you get the correct result. and we finally made some progress now. But area is not the only nasty thing that can give wrong answers, right? Distance is still something we need to solve in that way, and many other operations. And with my, no, I'm gonna skip the rest here. So, any questions? Thanks. Yeah. It doesn't exist yet at the moment. Jiro can do that subsetting. I don't think I even expose it fully. Um, Currently with Arrow and Geo Arrow, there's no direct way of subsetting. Ideally, you have formats that have a native spatial index attached to it, like flat GeoBuff is a format that has that. And ideally, we would make use of that. But with the whole spatial tree interface that we have now, we could try to actually implement it. What it didn't show is that if you now load something in geodata frames, the geometry column will automatically have an index attached to it. The drawback is that it's a planar index, so I didn't show it. It's slightly wrong again. Um, yeah, I'm following GeoPandas essentially, but hopefully it's more interoperable with the rest of the ecosystem. Anyone else? Yeah. Yeah. So for cloud optimized reading, so having a subset based on some intersection, you need a spatial index attached to the file in somewhere in front, or at least that you can easily read it. So you would, if you would read that file, you would only read the metadata and the spatial index, and that's it, lazily. And then when you do an operation like give me this within the bounding box, you would take the spatial index and indeed get a range of bytes that you need to get from the online thing. That's exactly how it would work, and you would need, I think Arrow can store a spatial index. It's mostly that there's no specification. GeoParquet has a thing or an experiment with an index, I believe. But these specs are evolving, and they're also roughly the same people that visit the SDSL workshop. And it's coming up with a good spatial index, and then just trying to adopt it. As soon as it's in Python or in Julia, I'd say happy there's adoption, there's cross-language support. Okay, thanks. Great. Okay, well, let's try to get a spatial index in. I think I have an experiment somewhere where when I talked to Kyle Barron about this, where I tried to compile all his stuff as a GOL package, but never fully materialized. Because our own Arrow implementation, uh, there's no Arrow C in Julia. There's no implementation like that. So that holds us back majorly. Okay. Yep. It's unit HTML.
Alrighty. Hello, everyone. I'd like to introduce myself. Um, I happen to also be the author of this Geometry Ops package that has been spoken about a couple of times now. And I wanted to just go over sort of the journey of how we got Geometry Ops on the sphere and the innumerable headaches that that causes. So for the purposes of a lot of stuff discussed in this workshop, um, the thing, oh, where's the chalk? the thing that is interesting that geometry ops does is polygon intersection. So let's say I have one polygon, looks like this. I have another polygon, looks like this. I want to get this polygon. And then once I have this polygon, I might want to find its area. I might want to find the length of its perimeter and so on. Um, and this is notoriously complicated to do even on the plane. And the nice thing about the plane is that you are only limited by the preciseness of float 64, which is itself, I would say, not that precise. When you get to very, very small differences between numbers, float 64 essentially becomes a grid. And when you have a line that goes from, let's say, this point to this point, the endpoints are all expressible in float 64. But something like this, if you try to do math on it, the numbers will actually snap to different places. And so for a point here, you may not be able to distinguish whether it's on the right side or the left side of this line without some clever tricks. So that we did, when Geometry Ops started out, and it started out as the polygon intersection there started out as a way to do lots of very, very intersections of very, very small polygons for simulation purposes. Um, but of course, as Martin said, we have lots of geometry which should be natively on the sphere, and so we need to treat that correctly. What does that actually mean? Let's go back to this unit sphere for a minute. Uh, when you think of latitude, longitude, you can think of that as sort of describing two angles on a unit sphere, right? Phi and theta, if you have seen those spherical coordinates. And so you use points on the unit sphere in, x, y, z instead of latitude and longitude. And then you need to create separate exact predicates for the intersection of two arcs on the sphere, for example, or which side of a line a point is on. And this stuff was actually solved by Google in, I think, around 2014. Or a bit earlier maybe, they published this library called S2, which had a lot of these geometry operations, and it also had a lot of the problems with exactness that it solved. And that's open source, Apache 2 license. And then there's this other library called JTS, Java Topology Suite, which is the predecessor to libgeos, which I think many of you might know as the sort of industry standard library to do these operations. But of course, those two only work on the plane. So like I said, you can see this figure up here. The green lines are what that quadrilateral looks like on the sphere. The purple lines are what that quadrilateral looks like in longitude latitude, if you just interpolate it in longitude latitude space, right? So the correct quote unquote answer is actually the green lines. That is the interpretation that one should have. So controversial topic, AI agents were great for this. Um, I was able to take Google's S2, take its predicates, get the actual intersection algorithm from JTS, which is very good for very large polygons and things like this. And we then, yeah, it's been about, I think, a year since I started trying to do this. We're able to port them to Julia, get them all natively implemented in Geometry Ops, tested against existing implementations, and we now have native spherical geometry. So by native, we had area of a spherical polygon for a while. That's pretty simple. But to get the intersection right takes lots of edge case handling. So I do have a couple of cool videos here that I wanted to show. So this is just a little video of how the polygon intersection process actually works. So you have these two polygons, A and B, let's say. First, what you need to do is you need to figure out, okay, what edges on these polygons could possibly intersect, right? And this gets into sort of spatial trees, which we'll get into later. Then you say, okay, I know these edges can't possibly intersect. I'm just not going to care about them. They don't exist for some cases. Then you say, okay, what are the points at which all of these edges from polygons A and B, where do they actually intersect, right? So this is called noding. Um, Now, one thing to note here, this is where you run into those float 64 problems that I was talking about. And that is true on the plane, that's also true on the sphere. I have a little page on Geometry Ops, which I can show later, which shows exactly how bad this gets. But yeah, this is part of where you run into a lot of issues. And so once you have these nodes, you basically split the set of edges into a graph, or a graph structure in this case. So if any of you are familiar with how certain video games work, they have these half-edge structures, where basically each edge knows where it came from and what its successors are, where they're going. So that's the structure that JTS uses, and therefore that I've also used in geometry ops. Then you label the edges by saying that, okay, these edges form something and these edges do not. And then you can walk the edges and build the result polygons. And you also figure out, sort of which way to route the edges and so on. So this is the final step. And this was all on the plane, right? So you can see we now have two, what they call rings or sort of individual polygons as a result. But we can go to the sphere, and this is just, I still have a little bit of time, okay. This is a bit longer of a video, but it just sort of shows some of the complexities on the sphere, and I thought people might find this interesting. So you have these two spherical polygons, right? The arcs between the points are all great circle arcs, so shortest path on the sphere. And just again to re-emphasize, right? There is a substantial difference between these great circle paths and the path that it would have been in latitude-longitude space. But this edge, or this path between these 2 points is actually just a circle on the sphere. It's a great circle, right? So when you try to take an intersection, it could intersect at one place, or it could intersect at the other end of the sphere. So first you have to establish which point in three-dimensional space is actually the correct intersection. So that's one of your differences. And then from there, things proceed more or less the same as on the plane. Oh, does anyone know what this means? Oh, oh, it's plugged in, I thought. It is plugged in. Yeah. Okay, so this is now showing the sort of the assembly of this polygon. And as a last step, I'll also show the difference between this spherically clipped polygon and a polygon that was clipped on the plane. This is US. I can take this out. Okay, perfect. Oh, okay, perfect. So the green one is produced by spherical clipping. The purple one is produced by planar clipping. It's a lot of difference. It's a lot of difference. Of course, on smaller scales, it matters a little bit less, but it's still quite substantial. Oh no, this restarted. Um, so let's see. If I could show one more video, I want to show also the importance of spatial indices here. So spatial indexes are just sort of ways to cluster polygon edges or points that are close together. Um, and by doing this, you can really accelerate the speed at which these computations happen, right? Because you throw away a lot of computations that never needed to happen. So this is the state of Massachusetts, right? This is on the plane for now. I have a spherical example as well. And what I'm going to do is I'm going to take a rotated version of that state because it's quite complex geometry. And what I'm showing here is basically how how we descend through these trees. Um, and so you can see that both of these geometries had spatial trees, but because we had those spatial trees, we were able to say, look, for this edge, I only care about these are the only edges that could possibly intersect, right? And you see that indeed it finds one intersection there. The camera movement is a little odd, but you can see the intersection that gets found. And so this is basically, if you don't have this and you try to do large polygon intersections, you're just going to be sitting there for hours and hours while while these extremely annoying computations end up happening. But let's now look at the sphere, right? Because we saw what happens on the plane, but how does this extend to the sphere? Well, one thing that we went over already is is this sort of idea of spherical caps, right? Um, little spheres which encompass some area, where the center of that sphere is on the surface of the Earth, and the radius is defined as some radius. But what you can also do is, because this is a unit sphere in Cartesian space, you can define three-dimensional bounding boxes in Cartesian space. And for some cases, like the hexagon, you actually want the circle because that's a tighter bounding box. But for these arbitrary cases, the 3D rectangle or cuboid actually is able to be a lot slimmer, right? While covering the same edge. So you have a lot less junk data, basically. So you can see how this sort of gets built up, right? These are all three-dimensional boxes, and then you build up this tree. And then, yeah, this is where it's very difficult to actually show what happens because there's just so much stuff on the screen. But you can see that the same advantage that we had on the plane is the advantage that we have here. So yeah, thank you. Just wanted to give a brief overview of how this all works. Any questions? Okay, Alex? Yes. Released as of last night. All of them for this particular thing, but I'd say probably around, I think the net diff was about 20,000, but a lot of that was like irrelevant tests and documentation and crazy comments, which get stripped out. I would say like the core of this is probably around 3,000 lines. Yes. Yes. You can do the bounding box on the ellipsoid. What you can't do is the edge intersection. So the reason for that is on the sphere, some kind soul was brave enough to try and figure out the exact floating point error that you can have and how you address that. On the ellipsoid, no one has done that yet, and it's not clear that it even can be done. So the best bet that we have is probably just slap an orthalic transformation on beforehand and live with it. Daniel? Mm. Yes, yes. So the leaf element in the tree structure in this case is in a single spherical arc. But you could have any leaf element, right? I do this for grid systems also. Simon, you had a question? Awesome. Okay, I think we are at about time for my talk. So we can start the community session about now, I think. So let's kill the recording. Can we leave the mic on actually?
Hello, everyone. Yeah, thanks so much for coming. And it's amazing to see so many familiar and unfamiliar faces again to JuliaCon. This, for the next 3 hours, including a coffee break, we will have the Earth System Science in Julia mini symposium with a bunch of many talks. Each of you were allocated some 10 minutes, but maybe you've seen this from the schedule that actually we had, I think, two dropouts. So what we decided to do is basically to give you all like 1.5 minutes more or so, meaning that these signs are probably a little confusing. And so we're not going to be super strict on this, but just to kind of like after 10 minutes or so, we might show you this one. But basically everyone is allowed to run over a little bit. Earth System Science in Julia, we wanted to, so we organized this together here with Lazaro and Jan, and we've done this, I think, 2 years ago as well in Eindhoven, as well as, I think, the year before that in Boston. It's always basically about getting everyone in this community together who does something with Earth System, especially the people that do a lot of like modeling, solving some kind of equations. We had the geospatial mini symposium earlier that is usually a little bit more focused on the data side of things, and we're basically more on the modeling side of things. So we hope to get everyone together, see what methods are we using, learn from another. And so there will be talks on atmospheric stuff. There will be talks on ocean stuff, on sea, on ice, as well as snow. So I hope everyone's going to learn a lot from another. And with that, I think we really would like to kick off immediately with Ingo from Avi. And do let me know if you want to have a little information of like how much time you have left, but otherwise I'll basically just like give you a little hint that you should probably wrap up. And then if you're really naughty, then I might use this one, but don't be afraid of it being red. We're not that strict on time today. Great. So the floor is yours, Ingo. Happy to hear your talk. And, sorry.
So, hello everyone, and yes, I'm Ingo Wohltmann from the Alfred Wegener Institute, and I'm talking about. Oh, sorry, not used to yet. That. And so I'm talking about the ATLAS chemistry and transport model. And chemistry and transport model, you might not know, it's similar to a climate model, not quite. And it's a model with a focus on the stratosphere. So my expertise is the ozone hole or the stratospheric ozone layer. And that was first focused on that, but it has also seen some extensions, like, for example, in the troposphere with convection and tropospheric chemistry a little bit. And one special thing is you normally think of climate models that they have grid boxes, and this is a Lagrangian model, so it uses air parcel trajectories and it just traces the trajectories and has an irregular grid of trajectory endpoints and not grid boxes. So that's something quite special, which not many models do. So what is a chemistry and transport model? So what we do is we simulate transport, mixing, chemistry, and microphysics. But what we don't do is that we have a dynamical core. So we don't look at the Navier-Stokes equations and calculate pressure or temperature, things like that. We take that normally from a reanalysis, so meteorological data like ECMWF data or MERA data or whatever we have. So it's actually quite an old model. So it's from about 2008, so more than 15 years in the moment. And it was originally written in MATLAB and C. And I have written that in Julia since about 5 years. And the reason for that was it was really not running very good on MATLAB. It's expensive. And we had all the version changes there, and it was not compatible with the operating system and so on. And also not really very fast. And one of the main reasons was also that I had really a speed up of a factor of 10, which I was very happy about because it's a slow model. Chemistry is just slow. Yeah, and it has actually been used in science for a long time. So there are about 20 publications, mainly done with the MATLAB version, but also some with the Julia version. So, and if you want to look at that, yeah, I have here my ORCID account and my publication list. Not quite sure if it goes online somewhere, if you can upload that, probably no. So that not everyone needs to note that. So that's again a little bit of the model overview. I already said something. So it's kind of a modular approach. So we have a chemistry model. Then we need some initialization for the chemistry from satellite or aircraft data. And then we have the meteorological data like temperature, wind, and some other things which we take from the outside. And then we have a transport model coupled with the chemistry model. And we have also some microphysics because we need clouds in the model. Yeah, and this is one first example of what can you do with the model. So that's a snapshot from a global model run, which of course run a lot of longer than only one day, and also a 3D run. And that's the ozone hole at 50 hectopascal for 2011, 1st October, as simulated by Atlas. The units here, that's parts per million in mixing ratios. So 0 is really the ozone hole, sink in the middle there. And that's Antarctica, as you can see. And around that, we have much higher ozone values. So that works quite well. It does what it has to do. And then I only wanted to bring two examples here because I'm a little bit limited on time. Something completely different is, for example, sources of the SO2 that enters the stratosphere. And we have in the stratosphere the Junge layer, so the stratospheric aerosol layer, which is important for climate, for the radiative balance, for ozone depletion, and things like that. And so we want to know where comes all the stuff in the aerosol layer. And yeah, that's the sources actually of the SO2 simulated by Atlas. Where does it come from? You can see it's a lot of SO2 from China, from India, so from anthropogenic sources, from air pollution. But there are also two spots here where you can see it's a volcano. So that's one on Papua New Guinea. And the other one is, I think, Popocatépetl. So So now a little bit more to the Julia side, it was more scientific so far. So it's in the moment just a bunch of code, so it's no package because I really concentrated on the science so far. So you just have to do an include, and then everything gets into scope, and you can just call the functions. And it's kind of a modular approach. So the different models, you can start them standalone. You have the full model, the full 3D global atmospheric model, which can run for months and with global coverage, which you can just call this Atlas, and the struct where you give all the options, and you normally have sensible defaults for everything. And then you can also call, for example, the air parcel trajectory model, where you can do individual trajectories. That's one example there on the right side, where you can see a single trajectory just calculated with a trajectory model, and you can also do ensemble trajectories and things like that. And you can also call the chemistry model standalone as kind of a box model, so zero-dimensional model. And for example, I show here on the right side the diurnal cycle of a short-lived species, that's NO, nitrogen monoxide in this case, and we can do things like that. And the output normally is in netcdf files because we don't want to do that in the Julia workspace. It's really a lot of output which you need, and so you save that to disk and then you later load it again. So some implementation details. Something is when you do a Lagrangian model, you have the problem that you have no numerical diffusion, so you have no diffusion at all, but you have some diffusion in the atmosphere, so you need to model that, which actually is an advantage over Eulerian climate models. And there is an algorithm in it, I will not go into detail, which actually can be tuned to observations, so that you can say, we have so and so much mixing in the atmosphere, and then we can tune it to that observation, which is a lot of better than in a Eulerian model. And we need to triangulate all our air passes for that because we have irregular grid. And then we need to trace the movements of these air parcels and see where there's shear and strain in the flow, and then air parcels are inserted or deleted, or mixing is done for the chemical species. And yeah, of course, we need the triangulation on the sphere for that. And that's one of the things which is maybe interesting. The other thing is, of course, the chemistry. And that's just written from a human readable text file. So we have just the reaction and then the reaction coefficient in there, and just a long list of all the reactions that we need. And then the nice thing about Julia is you can just generate the code and be fast there from this human readable file. And it's quite flexible if you want to add a reaction or delete a reaction. Yeah, that's really nice. Of course, many of you probably will know Catalyst JL, but I didn't get that to work for some reason, so I wrote my own parser that also works. So it's relatively simple in my case, so it was not too much work. And yeah, then I solved the equations with differential equations, JL with the Rosenbrock solver with different equations. So that's basically the implementation of that. So that needs to run parallelized because chemistry is really, really slow. There's a reason why you have no chemistry in climate models normally. There are chemistry climate models, but they are slower. So we typically run on about 50 cores on our Unix servers, and it takes about 10 hours or just overnight to have 1 year ready. So we can't really do 100-year runs or things like that. It's too slow for that still. That's 150-kilometer resolution, but that's fine for the stratosphere. So you don't really need 10 kilometer or something like that. So, and that's now my most important slide because it's really been a one-man project for a long time, and it would be nice if I would find some people who would be interested maybe to collaborate on that. Mainly, it's the problem in the moment is it's no package. It's just some code, and maybe it would be a good idea to turn that into a package, but that's not my area of expertise, how to do that. So if someone would help me there, that would really be nice. And documentation is missing because I use it for scientific work, and of course that's not priorities and tests, and some new features would also be nice. And it could even be coupled to a climate model if somebody would be interested in that. I don't know if there are climate models in Julia, real climate models. I think there are, but I'm not quite sure in the moment. One challenge for running that on a laptop or something is, of course, you need a huge amount of data files. You need all the reanalysis data, which can be really go into the terabytes if you want to do some more years, and all the satellite data for initialization. And that's a challenge. So that will not be that easy to do. And I really never try to run that outside of our server, so don't know if that even works. So. And finally, that's the source code. So if somebody is interested, we have a GitLab server at RV, and that's probably protected. I don't think you can reach it from the outside. So I've put a snapshot for the conference on Zenodo so that you can read into the source code if you are interested. So that should have, yeah, that's the last. Okay. Questions? I would say it's not too small of a room. Maybe we can start and then we can repeat the question. Yeah. So can you run your model in reverse mode? Yes, that was actually done. Okay. Can I run the model in reverse mode? Yes, I can. So you can run the trajectories forward and backward. And that was actually done with backward trajectories. They were started in the stratosphere and then go down to the troposphere. It's much less effort than the other way around because you have to skip so many trajectories which never reach the stratosphere. No? Because it's only 10% of the mass of air. And one more question. Well, I use a Rosenbox solver, which is kind of recommended for chemistry. So if you read into the papers, mostly say use a Rosenbox solver, and that's for stiff chemical equations. I think even differential equations says that on their homepage, use a Rosenbox solver, and that works fine. So it's fast and reliable, so it doesn't give any strange values for the chemistry. So that's quite okay, I think. Yeah, 70, 80%. So yeah, so one time step, so that's 12 hours takes about 60 seconds, I would say, and about 50 or 40 seconds are chemistry, and the rest is mainly reading in the data.
Oh, fantastic. Let's thank Ingo again. And then while Patrick's setting up, we have the next talk by Patrick from Davos about snow, about his project called Helmut. Why is it not called Patrick?
I can explain. Okay, so I'm going to present to you Helmut.jl. It's like a new age flexible snow cover model. And as Milan already asked why it's called Helmut, it's named after a mammoth that was found in Paris a while ago. And the French thought it would be a funny name. And then also the mom of my colleague drew like a logo, which is this one. And it stuck because it's just very, very cute. Um, it was developed at the Institute of Avalanche Research in Davos together with the Snow Research Center in Grenoble in the Ivory project. And before I start, just to clarify, by snow cover model, I mean like a very detailed stratigraphy model in 1D of the snowpack. Why do we need such a thing? The first thing that pops to mind are avalanches. And for avalanches, it's not just important how much snow there is, but also how the snowpack is structured. I just brought two examples from two sites where one in purple, an avalanche was released. In blue, it wasn't. On the y-axis, you see the snow height. And on the x-axis, you see the hardness. And you see the avalanche side has a very, very weak snow base. And the stable side has like a gradually decreasing snow depth. And you wouldn't know if you didn't go in the field or you don't model. The second thing is flood forecasting, because also here, it's quite important to know what actually happens inside the snowpack. Here you see in the top, you see the runoff from from the whole snow cover, and the bottom you see the density, the liquid water content, where brighter colors mean more liquid water present in the snow from March to like June. And you see, like even though there is liquid water present, it doesn't necessarily immediately run off. You have like lags because of new snow, temperatures, or whatever. But the question is also, why do we need another model? There's Crocus, which is the French model used in weather forecasting mainly. And then there's Snowpack, the Swiss model used a lot in avalanche forecasting and also lately in weather forecasting. The problem is both are just huge monolithic models. They're super hard to like change, extend, to understand. And like recently there were like some new physics that were found out, and the new models were pretty much unable to incorporate those. And then it's super hard to prototype new things. And this is like super hard and super problematic in snow science because a lot of things are like empirically parameterized, and like stuff is still like physics is found out that has not been there before. So you need to incorporate this, which the older models make super hard. Now to what do we actually do in Helmut? So first we look at the radiation budget. Like from solar long wave radiations, we look how it is absorbed in the snowpack. Then we have some atmospheric processes, which are all forced by external data. We don't have a weather model, it's pure snow. But also here we have like rain on snow, like snowfall, wind that drifts, blows away snow that compacts it. And then obviously also all the processes in the snowpack itself, where like snow can melt, the top, the bottom, in the middle. It can refreeze, it can grow crystals, whatever. Super complicated, but we managed to solve it rather well. On the Julia side of things, how it actually looks like, we try to make it as flexible as possible. So pretty much everything is type-based, based on parametric types. For example, here, you would set up like the physics in the core physics module, where you choose what type of energy conservation you choose. You can change different processes together so that you, in the end, have like a full compaction, whichever way you like. Then you choose like
the material models actually used so far, there's only snow, soil, and like a skin, which is just the interface between the snow and the atmosphere pretty much. And then we initialize everything, where also number and like vector types are like parameterized so that we can run lower precision at some point, hopefully also differentiable, and GPUs, which was not a priority, so not yet fully functional, but we're going there. Then in the core, we have pretty much three functions. The first one that handles like output writing, um, configuration, initialization, it steps the whole season. Then we run for each time step where we handle like forcings, like apply certain stuff and like convergence criteria. And then the actual Newton iteration happens in the end where we assemble all the equations in one Jacobian. So we solve everything coupled. We apply all the boundary conditions and then solve it. And we did it in such a way so that hopefully it's easy to like incorporate in like different use cases where you might not necessarily want exactly the same type of output handling that we have or like the same kind of like application processes. Also the physics, try to not hard code too much, where like the variables that we track, the bulk variables, the physical processes itself, and also the materials are abstract types, where you can super easily subtype. For example, here I brought an example on how you would implement a new compaction, which just means like the settling of the snow under its own weight. You dispatch, you create a new dispatch for the main assembly function, and then call it in your physics model, and everything else stays the same. Also, more important probably to a lot of people here, how you would couple it. There's like two ways pretty much. The first one is through the existing forcing data that we need to run the model, such as surface temperatures, wind speeds, and whatever, and then just choose one of the already implemented boundary conditions. But also since the boundary conditions are flexible, you can also just subtype those and do whatever you like to couple your model. Now to what actually have we achieved so far? I brought a couple examples. The first one is from Weißfjoch, which is our test site in Davos, where snowpack, it's like the reference site for snowpack. And in the top, you see the snow height over the whole season. And you see it matches really, really well, actually. In the bottom, you see the densities of both first Helmut, then snowpack. And you see snowpack is a bit more detailed, like higher colors mean higher densities because it was tuned for avalanche forecasting and they're like the very specific densities make or like structure make a lot of is super important, and we didn't port all of it. The second example is from Crocus, in comparison with Crocus at Col de Port, which is the reference site for Crocus, as you might have guessed. And also here you see in the top the comparison in the snow height. Also here it matches very well, except for the end of the season where we have a problem with melting that we're trying to figure out. And the bottom you see the densities actually match better than before because that is mostly like Crocus parameterizations in there. The cool thing here is now that what I just showed is not just like an implementation of Snowpack or Crocus and Julia and you just choose, but this example here is pretty much a full Crocus port in Julia, pretty much. And the first one, the Snowpack comparison, was a mix between Crocus, Snowpack, some new parameterization, and just shows that the whole flexible framework actually works quite well. And also what is cool, you can do stuff that might not make sense. You want to try out stuff. Here I brought an example of what happens when you turn off the whole compaction, like snow doesn't settle anymore. And you see it just accumulates, it does something, it works, doesn't make sense, but it's cool to try out. So what are we gonna do until we release the model? Hopefully by the end of the year. We still need quite a bit of documentation and examples. We want to try to improve GPU support so that it's hopefully able to run on GPUs. And then I have some ideas on how to make it differentiable. Don't know how far I'm gonna get there, but hopefully far. So if you have any ideas, feedback, very, very welcome. Yes, so, oh yeah, sorry. The question was, in short, how do glaciers fit into this model, right? Yeah. And essentially also, since the materials are kind of like flexible, so far we only meant to implemented snow and soil because that is what is best known, but in principle, it's super easy to implement a new material that would be like something like glacier ice. and then you would only need to define how glacier ice handles soil, like radiation absorption, stuff like that, and thermal diffusivity, and then it should work as well. So, did you hear the question? Like, I didn't fully hear the question. Sorry. Yes, in a way. Like we tried to make it so that it is easy to use and kind of like a snow modeling library almost. So you can just pick the parts that you want. The problem is a bit more also that it's supposed to be like also like like a research level, research grade snow model, right? That you can compare against. So the focus was more on like that it actually works really well. So that part is like somewhat left behind. I hope like it's supposed to be going there. They can also use it then in other models, hopefully.
Amazing. Then let's thank Patrick again. By the way, if anyone has a laptop without an HDMI, I think the technical team, they also have a to USB-C converter. So just let us know. Oh, it's lying there. Perfect. Yeah. Great. Well, Irmgard setting up. I'll give a little quick introduction because we're going back from snow to the atmosphere with some gravity wave modeling. And yeah, so Irmgard is going to present this. Thanks so much for presenting, and you'll get the microphone.
Thanks so much. My name is Irmgard Steiger. Sorry, I got married and changed my name. So I'm a PhD student at the Goethe University in Frankfurt, and in our group, we're working on gravity waves, and we're looking at idealized modeling, and we're using pink flow, and that's a model that we're currently developing in our group. Before I start with the presentation, I'd like to give one huge shout out to Felix Jochum. He did a lot of the heavy lifting when it came to translating this code from Fortran to Julia. And then very huge thanks to Marco Attiano, Arpit Babar, and Henrik Renoja from the university in Mainz, because when we were Julia babies, we had no clue what to do, and with their input, we now have a model that is efficient and we can use for our research. So I would like to start off with a overview of pink flow. So pink flow is a pseudo incompressible flow solver. It's an atmospheric flow solver that we use for idealized modeling, so we don't like have a sphere or anything like that. We focus on atmospheric waves and their interaction with the large-scale flow, turbulence, tracer transport. There are other people in our group who are looking at, for example, ice microphysics. And it's available in the general registry, so you can just download it whenever you want. It's optimized for HPC use, so if you want to do high-resolution simulations, that's possible. We use it for not only research applications, but also for teaching. So also there, it's easily usable for students within like a tutorial or so, and it's actively being developed. So if there's any issue or so that you find, you can mention it and we fix it as soon as possible, or there are always new features that are being included. And I'd like to start with this little simulation that you can see what type of atmospheric waves that we're talking about. So what you can see here is this little mountain. It's very small, and we initialize the atmosphere with a constant zonal wind. And over time, you can see that there's this wave structure that is an orographic gravity wave, and in color you see the vertical wind, so you see this wave structure in the vertical wind. I would like to give like a quick overview of the scientific capabilities of pink flow. So we not only have we have the Boussinesq equations, those are the nearly incompressible equations. Then the pseudo-incompressible equations, those are in between the Boussinesq and the compressible, because they are soundproof. Soundproof means that acoustic waves have been filtered out. That allows for larger time steps, because in atmospheric modeling, you most of the time do not need acoustic waves. And then finally, we have the compressible equations. For the parametrizations, currently there is a parametrization for small-scale gravity waves and for turbulent kinetic energy. However, a feature that will be added soon would be, for example, ice microphysics. So there's always an extension of parametrizations. And then for the discretization, we've got a semi-implicit time step that allows us to use larger time steps than if we were just simply using a Runge-Kutta, meaning it's, again, a bit more efficient. We've got we're using a finite volume, and we've got terrain following coordinates with vertical grid stretching. So if you want to have a topography, which you can use any arbitrary topography that you would like, that is possible with PinkFlow. And we've got periodicity in X and Y and a solid wall in Z. And to demonstrate our two different methods that how we're using PinkFlow. So on one hand, we always do these wave resolving simulations. So those are high resolution simulations. Those always act as our, in a sense, reference or truth. So I've got a simulation here. You cannot see the mountain because it's so small, but you can see that there's this gravity wave field that is being emitted. That is a 3D wave resolving simulation. On the other hand, say you would like to have simply a coarse resolution simulation because you would not like to have something that's so expensive. We also parameterize gravity waves. I'll get to the gravity wave model in 2 seconds, but you can see this is exactly the same setup, but instead of resolving the gravity waves, we have these ray volumes, so these little blue packets that are propagating upwards. And it's actually a very, very physical approximation of gravity waves, and this is coupled to the large-scale flow. So this gravity wave parameterization that we're using is MSGWAM. That stands for multi-scale gravity wave model, and it's the next generation gravity wave model because if we look at current parameterizations, those are the ones that are in all the climate and weather models, they assume that the gravity waves only interact with a balanced flow. So, and we have a single column and steady state assumption. That's what you can see in this figure all the way on the left. So the gravity waves, in a sense, instantaneously propagate throughout an entire column, and then the entire gravity wave impact is just simply vertically integrated. Not very physical, but quite efficient. And MSGWAM allows for an interaction between gravity waves with unbalanced flow, and MSGWAM is a ray tracer in 6-dimensional phase space, meaning that the position and the wave number of the rays can, or of the gravity waves can change with time. And we allow for horizontal and vertical propagation, so 3D propagation and transients. Now, in the center, that would be if you would only have 1D, that would be a cheap version of it, but you can see these little rays, those are the red dots, and they can move within a column up and down. And then all the way to the right, we've got the 3D version. Again, these rays can propagate in all 3 spatial dimensions. Now, a quick overview of the implementation in PinkFlow. So we have an extensive documentation. Every single function is thoroughly documented, even experimental features. There's a whole description of what the equations are with references and all of that. It's quite efficient due to the parallelization. We've got 3D parallelization using MPI, so also not only in X and Y, but also in Z. Parallel I/O using HDF5, which is why we have not used NetCDF yet, which is the standard in this field. And we also have HPC run scripts in case you would like to try it out on whatever HPC that you're using. The model also supports ensemble runs in case that's something that you need for your research. And it's very customizable because the input parameters or the initial setup is defined via functions. So let's say you would like a wind that has a very specific jet at a height of 10 kilometers or whatever, then you just write a function that describes this jet. Or the underlying topography should be according to a certain function or according to a certain input, or the sponges. All of that is customizable. And then there's also a Mackie extension for visualization. So if you would like to, let's start off with the configuration. We've got these name lists. Very similar to what you'd always have, like, for example, in Fortran. I don't know if you're, like, familiar with those, but you'd, for example, set all the atmosphere parameters, or you'd set the domain size and all of that. You'd give that to nameless, and then call the integrate function that runs the entire model for you. Now, within the model, there is the composite type called state, and that contains the entire model state, so all the prognostic variables, all the initializations, and so on and so forth. And every function, or almost all functions, simply rely on state as an input, meaning if you want to extend the model, create another function, you just create a function, give it state as input, extract whatever variable you need, manipulate it, and then that's it. And then finally, plotting is, here would be, for example, a function that we've written called plot output if you want to plot, for example, in this case, the vertical wind. I'll give you a quick introduction of how you get started with PinkFlow. As I said, it's available in the general registry, so you just simply install PinkFlow. And we have simple pre-made examples in the second code block. You can see where we are using the periodic hill test case, which the result is given all the way on the right. That, as you can see, we have this gravity wave field due to flow over periodic hills. And then finally, if you would like to have your own configuration, this is just an example of how you'd get started. Let's say you would like to use the compressible dynamic equations, and then you would also have an initial zonal wind, so that's where we've got initial U, that is 10 meters per second, and then you just put that all into nameless, and then give that to the integrate function. That runs the model. There's no output, or there is an output for that, but it has no physical meaning in that sense, so I didn't show anything here. Finally, if you would like to have the actual source code, then you can go to the first QR code on the left, and the entire documentation you can find here on the right. So thank you very much. I'm very open for questions.
You mostly showed now the 2D side, but that model is also able to like, get the 3D, like you never like it's not the focus, so you always have like a periodic box.
Yeah.
Question?
Oh, okay. So exactly. So we have periodicity. If you're asking if we have periodicity in X and Y, any other?
But sorry, whether would you also be able to like simulate actual like low and high pressure systems and how they would interact?
Yes, you could do that. We do only have a constant Coriolis parameter, so that used to be in the Fortran version, not constant, but that was a weird function that we never tested. That's why. So it's just a constant Coriolis parameter. But apart from that, it's periodic in X and Y, but you can do high pressure system, low and all that. Yeah.
Then swap over to Sarah. Yeah, thanks again.
captions that we have available, the kind of grids that we support, but also a lot of the software, basically engineering and the possibilities that you see, that you will also see featured in my talk today that go far beyond the Fortran version. And yeah, and with basically our fast and user-friendly interface, you're able to get a atmospheric simulation very quickly. So let's get one quickly. This is basically done in just 4 lines of code. First, you have to define the discretization of our model. That also sets the resolution. This we do in the spectral grid object because it's a spectral model and it has a spectral grid. Then we basically construct the type of model that we want to look at, and we could also configure it. So this is in this case a primitive vertication wave model. Then we do all of the pre-computations and allocations to have a simulation object, and then we can run it, and then also plot our results. So here's here global simulation and the specific humidity of one of these primitive equation models. The model itself also isn't just in GCM. Speedy weather also comes with some other parameterizations included for the other domains for idealized climate ones. So basically very simple parameterizations like a slab ocean, a bucket land model, or since quite recently, a thermodynamic sea ice model. And here you see a nice illustration that one of our colleagues made with this of the sensible heat flux that is exchanged across all of these components of these then idealized models of these domains and speedy weather. If you want to go beyond, though, these very idealized components, speedy weather is also part of numerical Earth. And within numerical Earth, we can also use speedy weather to get really comprehensive climate simulations as well. Numerical Earth is a framework and also community for simulating the Earth model, the Earth system at all scales. So then numerical Earth in this case handles the component communication, for example, the interpolation, the fluxes that are in computations that are exchanged, and also handles the time step orchestration between all of these different components. And which components these are, you see in this very preliminary coupling, where you see basically how we couple together then now speedy weather with ocean shenanigans, clima, sea ice, and terrarium, the land model that you'll hear about in the second part of the session. And there you see the temperature from the atmosphere, you see the heat, the fluxes exchanged between the ocean and the atmosphere, the ocean temperature, the sea ice, and the soil temperature of the land as well in this nice little animation. But this is also still work in progress. This coupling isn't really perfect yet. Then a lot of time that we spent actually now also recently on making this model more performant on GPU, hence also mentioning this on the title. Initially, speedy weather didn't run on GPU, and we basically now optimize it much more for GPU usage. There we basically identified the performance bottlenecks for the performance that are primarily our transforms. We batched together a lot of the transforms. We used CUDA graphs, and in this way, then we also were able to accelerate our model on GPU very nicely. If you want to go hear more details about this, Milan will have a separate talk about this on Thursday, so tomorrow as well. We currently also work on like further acceleration also with Reactant, but this isn't quite yet finished. And there you see basically that we already get throughout the bank and throughout our spectral resolutions available in low resolutions and in high resolutions, a very good acceleration with the GPU in green compared to different CPU architectures already. Aside from the GPU, as you also already saw in the title, another really main aspect of what we want to go for with speedy weather is also the differentiability. And for this, we use EnzymeJL. And with recent updates, both to Enzyme and Speedy Weather, we can now really also support actually all differentiability modes, so reverse mode differentiation forward, and also reverse over forward or forward over reverse, which wasn't previously possible. And while the gradient compile times of the gradient are still relatively long with 10 to 15 minutes, this is still already much lower than it was before. So this is workable. But also because of this, we also work on basically further adaptation of Reactant, which will also accelerate this as well. Yeah. And the reason why we actually want to have this aspect and why we want to have a differentiability of our model is that we want to work in the future really towards having speedy weather as a model that can be a playground also for hybrid machine learning, basically combining machine learning with a process-based model. And we already started a little bit with this and also started a little bit with using the differentiability. On the one hand, we have it for using it for sensitivity analyses. these kind of results I will not show you today. Then we started using it for calibrating our model, and then also for starting some neural network parameterizations for our model as well. So one of the first aspects I want to show you here is basically some work that we've done together with our student Niklas on calibrating our model with the differentiability. Niklas will also talk about this in more detail in our talk here on Friday. But basically, because every climate model and speedy weather as well has exhibits significant systematic biases due to its parameterizations, we can use the gradients, and we can use gradient-based optimizations to reduce these biases when we basically learn from an objective function or from data to calibrate it against. And this is what Niklas has done with our shortwave radiation model, where in the middle you see the bias before training, and in the right-hand column you see basically the reduced bias after he was done with his calibration scheme. But as I said, also the other aspect that we also want to tackle with speedy weather is that we really want to have speedy weather as a playground for testing new ideas for parameterizations, but also new ideas for hybrid machine learning. And one important step for this was also that we revised our parameterization system and made it much more modular and much more accessible also for users. So users can now define parameterizations without us asking. They don't have to fork the model. They can basically just do it in a script. You see basically this parameterization system that we set up, where you in a struct basically hold all the parameters of the parameterization. Then you define a function of what variables this parameterization wants and it needs to allocate. And then you define one function there that does the column-wise compute of the parameterization. And this column-wise compute then can also incorporate a neural network very easily. And this is also something that we already experimented a little bit. This was work that was now done by Greg, one of the PhD students at University of Oxford, where we basically now started to incorporate also neural network-based parameterizations in our model. One of the first examples there was a parameterization of the surface roughness, where Greg was learning the surface roughness from error 5 data. And then we put this also already now into our basically distilled version of this neural network, a distilled version with symbolic regression, now also already into our model as well. Here you see some highlight figure. If you want to know more about this, Greg will also have a talk a bit later today. I think the last talk in the session, he will go into more detail on this. So to wrap up, what I showed you is basically a lot of the progress that we made with speedy weather in the last year. We included more parameterizations. We have now uncoupling available also for comprehensive simulations with numerical Earth. We massively improved the GPU performance of our model. We refined the differentiability and also used it both for calibration, and we also incorporated the first machine learning parameterizations in our model. And with this, we really want to, basically make also speedy weather really available, as I said, as a playground also in the future for these hybrid machine learning approaches in atmospheric science. Yeah, thank you very much. And here you see the links both to the model, but also to a research article that uses not only speedy weather, but also Sarah's work and also work on shenanigans as well. Thank you very much.
Time for one question. Yeah.
The question was whether we come close to the performance of Icon or other big models, or if it's more a playground. To be honest, I don't have a good comparison to like really the performance at these resolutions that we tested at Icon. I can't give you a really good performance. I think on the GPU performance of these relatively coarse resolutions where we are still there, we are really comparable with them. It's just a matter that basically Icon has also then parameterizations available to go like in much higher resolutions that we just don't have available, and that we also don't see as like, we don't have a huge team of people working on it. And there, yeah, we actually really see this more than as a playground to enable basically, for example, easier integration of machine learning to learn these kind of parameterizations than where we don't have huge teams available that would integrate them into speedy weather. But purely from the performance, I'm actually not so worried, but I also haven't made a proper comparison. So that's just my intuition.
Thanks, Max.
to continue our session. Okay.
Fantastic. Welcome back, everyone, to the second part of our Earth System Science in Julia mini symposium. It's 4 p.m. now, so we try to run until 5:30. As already a reminder, at 5:30 there will be the photo being taken. So at 5:30, I think everyone is supposed to run over to the Alta Mensa, so where the registration is, and I think then on the stairs or so we take the picture. Otherwise, we have another 6 talks, I think, now in the next 1.5 hours or so. And the first one, I'm introducing Jan. And Jan does some fantastic ice sheet modeling, like it's Lego. So hopefully Lego isn't listening and try to sue you now. But I hope it's playing with Lego is fun, right?
It is, yeah. Well, I'm very happy to be here and to present this new work to you. I will say the title is a bit of a scam. Not because it's not true, just because it's not the focus of the talk in the end. But that's just the way it is. Sometimes you send something and it ends up being something a bit different. Um, I want to focus a bit more on the science of ice sheet modeling and what this unlocks. And to understand that, first I want to show a bit where things stand. And it turns out both Greenland and Antarctica have been losing mass over the last decades. As you can see, for Greenland, it was quite all over the margin due to surface melt. Whereas for Antarctica, the pattern is much more concentrated in the western sector. And that's because below the ice sheet at its interface with the ocean, there was an introduction, like an intrusion of circumpolar deep water that is particularly warm and that has driven the melt from below. Now, the question is, what happens with all of this in the future? And to do this, we proceed in the following way. We just take the CMIP models and we force ice sheet models with them here until the year 3000. And as you can see, Antarctica becomes a very large, but also very uncertain contributor to sea level rise. In low emission scenarios, you get somewhere around 2 meters by the end of the millennium and reach already quite before, actually. And for high emission scenarios, it ends up being sometimes as much as 14 meters. To put this a bit in perspective, I guess maybe for you it already sounds like a lot, but we have about 1 billion people living between 0 and 10 meters above sea level. And that's without mentioning all the critical infrastructure, so basically it would affect all of you. Um, but of course, what's bombing about this picture is the huge uncertainty bar. I don't know how anyone can be satisfied with this. So we aren't, and the usual narrative in ice sheet modeling is, well, then we just paleo constrain things. Do we? Is the question, because in the end, when you run paleo, you do end up having a much coarser resolution, and that influences the ice flow, but it also influences all the parameterization that you're choosing. Furthermore, ice sheets are a boundary value problem, but we tend to have boundary conditions that are not particularly comprehensive. And then 2 final points. Of course, hand tuning is the best tuning so far in ice sheet modeling, but it just turns out to be neither optimal nor reproducible. And finally, the lack of modularity means that sometimes we still have quite outdated physics, as was already mentioned before, regarding snow modeling. Now, Julia and in particular Pagos can improve all of that by using parallelism as much as possible. What we're doing here is mostly finite difference to solve our PDEs, and that's really helped by packages like JME, kernel abstractions, etc. Of course, we want to develop a bit better boundary conditions, be able to do AD, and finally, also dispatch our way through life and be happy modelers and users that can extend the package. Worth mentioning, we already have ice sheet models in Julia, but none of them really targets the paleo time scale, nor the continental scale. So the goal here is really to fill this gap. And for you to understand a bit what is it that we're solving, I just want to go briefly through the balance equations. First, you solve for energy. This gives you the ice temperature and the viscosity, which plays into the momentum balance, giving you the velocity, which in turn feeds into the mass balance via the advection. The ice thickness feeds back into the energy. The internal production, heat production does too. And finally, the ice thickness field alters the driving stress for the momentum balance. And so you end up with 3 highly coupled and nonlinear PDEs, with the central one being the main computational bottleneck. So that's the rough picture, and because that's the main obstacle, I want to concentrate a bit on the momentum. And basically, what we do is simplify this into a Stokes flow, and then into further simplification, sometimes changing the dimensionality of the problem from 3D to 2D. And back in 2008, there was this cool benchmark experiment. So you have a bumpy bed that is tilted, so ice flows from left to right. And when you perform a cross section, as you see here with the dashed line, what you obtain is a surface velocity. And the Stokes model, which is kind of the golden standard in ice sheet modeling, give you, depending on the resolution, this shaded area here or this shaded area. And Blatterpatain, which is a simplification of it that we implemented in our code, follows it quite closely regardless of the resolution. It's not exactly the case for DIVA, which is a depth integrated approximation, but it's good enough for the continental scale, and so I want to show this. You can apply DIVA with a linear solve, or solve it this way. The only problem is then you get quite bad GPU scaling. And so what we do is apply the techniques that were developed mostly by the people in Switzerland. So Ludovic Ress and Ivan Utkin, I think, might be in the room. Thank you for paving the way for all of this, because it was really a great help. And then suddenly you can somehow be worse on CPU, but be much better on GPU. And I will stress that all of these numbers are just illustrative. You can probably get way better performance. It's still work in progress, but you see that you can solve the momentum balance in about a second on 4 kilometers. And that's something that's really needed in continental ice sheet modeling. Now, the part I showed so far is really just the dynamics, but this interacts with other subcomponents, the topography, the thermodynamics, and the material. And you see, because of course we define abstract types, and then via concrete subtypes, you can easily choose how you want to represent things. And all of this, is essentially then or feeds this grid model simulation, and finally run or step architecture that is very typical for models in Julia. But we face another problem, which is, since it's a boundary value problem, you put some trash in, you get some trash out. And so how do you improve this? We try to co-evolve a small ecosystem around Pagos called Cryos. And the idea is to, develop for now the subcomponents I've highlighted. Ask me about those I won't be able to present today. They're really cool, but I can present everything. And for now, I just want to focus on the shelf ocean cavity, because as you've seen at the beginning, for Antarctica, that's the main source of mass loss in the last decades. And so to represent this a bit better, what we've done is to port Ladi, which is a Python code, to Julia. What does it do? It tries to represent this mixed layer below the shelf base at the ocean interface, modeling also its temperature, salinity, and velocity, to, in the end, compute the interaction at the ice base, being the basal melt. And so what you will see now is a small example of these variables for Cross and Dodson. This is this little region in red here. And you see that when we run at 500 meters resolution, we get a really nice turbulent flow, which is actually the high resolution feature that is happening at the ice-ocean interface, and that would be very difficult to solve with a classical ocean model. All of this is particularly nice because we get very similar results to the Python version. There are still small differences that I'm figuring out. But most importantly, we can port this to GPU and basically get an improvement in computation time, which is about a factor 100. So all of this is exciting. We can have fast representation of the ice flow, but also of its boundary conditions. And to conclude, well, we have the groundwork for this high-performance paleo timescale ice sheet model with its small surrounding ecosystem. AD is underway. I didn't have the time to show this today, but we're already working on that. And of course, the user friendliness is going to be a big aspect of this. And I think it's really pleasing to see on the left the observations and on the right what we've modeled and see kind of a really nice match between both. And with that, I'd like to thank you.
Questions? Don't be shy.
So the question is, how easy is it to couple something like this to speedy weather? On the long term, it would be the idea. We didn't try so far. And especially because in this kind of co-evolving ecosystem, we would have a module that deals with the surface mass balance, the snowpack. All of this should be quite easy to couple, especially because we're kind of complying with the same structure in terms of the whole philosophy of how the package is designed. So it should be really easy. Yeah. The other question is how to calibrate it, but maybe AD is a big help there.
Just like on the last slide that you had,
Mhm.
it looks like the kind of like, I think it was the ice flow that reaches the interior of Antarctica. It just looks like you're basically just like
Yeah. No, so that's a problem of color bar. It's just like our color bar is not exactly matching theirs. So yeah, but apart from that, I think it's really comparable. Yeah. Yeah. Okay.
cool. Then
Thank you.
and as the next speaker, I promise you, you haven't seen that person before. This is Brian. Uh, no, Brian is unfortunately not here. And so Max is giving Brian's talk now on terrarium. So we already heard a little bit earlier about the land model terrarium. And so Max is going to give a little overview about the state of terrarium.jl.
Yeah, thank you again also for having me twice, basically, and now presenting about Terrarium, as Milan already introduced. Brian was originally supposed to give this talk, and I'm stand in here to showcase the work that we've done together, also with other people in our group, and with Olivier from Ghent, who also is another contributor to Terrarium, and our work with it towards a fully differentiable and GPU-accelerated land modeling framework at all scales in Julia. We started this not quite a year ago, so this is still relatively new framework, and Terrarium is, we see it as a modeling framework for GPU-accelerated and fully differentiable land modeling in Julia that we base on oceananigans. And now you might immediately ask, why do you base a land model on an ocean model? This might seem pretty counterintuitive and paradoxical. But of course, oceananigans isn't just an ocean model. It is also a state-of-the-art GPU accelerated finite volume framework, computational framework. So we can use this also to basically do the finite volume computations that we have in a land, typically in a land model, primarily in the soil for the soil hydrology and soil energy dynamics very well with the FEM solver for oceananigans. We have them then already in a GPU accelerated way, in a way that is also compatible with React and an enzyme. And we also, with this choice, also facilitate a relatively easy, basically roadmap towards coupling it to atmosphere and ocean models within numerical Earth, speedy weather to oceananigans, and to the other models in the community. Then, of course, you also may ask, why do we really need another land model? There are already a lot of them. And the first point there is, I think that here in this room at JuliaCon, I don't have to tell anyone, a lot of existing land models have very high engineering barriers, especially those programmed in Fortran, where it's very hard to basically maintain these over a long term, get students which can actually work on them. They also often lack basically modern software engineering practices. So this also belongs that they also often lack GPU acceleration, which is also something that we care a lot about because we want to have high resolution, fast GPU simulations in a completely coupled also GPU model. And the other thing, which is a bit more unique than also for Terrarium, is that we really also want to exploit the potentials of differentiable programming and hybrid machine learning. Many land processes are very heavily parameterized, For many of the land processes, there are also no like real fundamental laws. For some, there are. So this really offers very good opportunities to also learn some of these processes from data and basically enable a hybrid model that can learn with differentiable physics together with machine learning. So yeah, as I basically was already alluding to a little bit, our target applications then for Terrarium are primarily the integration of data-driven components into basically hybrid land and ecosystem model, then also like global calibration, uncertainty quantification using these gradients, and basically always from the start on also thinking about this, how this can be integrated in a fully GPU accelerated, complete, basically comprehensive Earth system model. So now a little bit about the design that basically we made to design our model. Well, this you have to know that land surface models like this are primarily column-based or like point-wise models in which each column is computed independently. There's just very little to no interactions between the individual columns of the model. So you basically see there in the structure, we have basically the Terrarium time stepper that calls a model with different processes defined on it. And these processes launch kernels with kernel abstractions. And because the different columns are independent, we can basically just roll out the grid, and each basically column gets a different thread of the kernel, a different shader of the kernel. And within each of these, we have basically then all also vertical layers, for example, vertical layer of the soil, in the future then also of the canopy or other basically inline processes. One also thing that is very important there for us is that we really have a strictly basically formulated this in the form of continuous dynamics, in the form of differential equations, which seems very natural for people coming from atmosphere or ocean, but unfortunately isn't very natural for land modeling in a lot of ways. Then also we can very easily take basically then the atmosphere in the loop, for example, speedy weather, but also other atmosphere models potentially. Here we also basically already have sketched that we could also use downscaling for this. This is like something that we also want to look into, like the research that we do with this, using a dynamical downscaling there in the loop as well. Here you see an example how we can actually set up and run a model. This again goes very similar in this very similar interface that I also basically just showed you for with speedy weather, but that's also adheres where also like all shenanigans is a part of how this kind of like works, where we first set up the discretization of our model. So here the grid structure and the device that we want to run our model on. Then we construct the model, you call the land model. Then we set here the boundary conditions. So here we prescribe a surface temperature. Then we initialize our model, basically pre-compute and allocate everything that we need, and then we run it. So this is the general interface. And as I said, we basically are a relatively new development. So we just released the first real version on GitHub and the Julia registry. That includes the soil energy and soil hydrology, surface energy balance, also then with, for the coupling as well. Include a simple snow model, surface hydrology, and basically a vegetation carbon representation that is based on the Paladin model, but also still work in progress, especially on the vegetation. We still have to work in the future because this is a little bit incomplete at the moment. Here you see then also like some results of actually where we also see already one of the advantages of like why we buffer with this, that we really get very good performance with this model on GPU compared to CPU, where you see in yellow the GPU and compared to the CPU results, and you see basically these orders of magnitude, the order of magnitude difference, especially if we go to very high resolutions where the GPU just massively outperforms CPU simulations. And then, as I basically said in the beginning, one reason why we also bother with this is also that we from the beginning on want to think about also coupling to other Earth system component, after Earth system components. So here you see a coupled simulation with speedy weather. On the left-hand side, you see the soil temperature, where you also clearly see the daily circle. On the right-hand side, you see the snow depth, where you of course don't see such a strong daily cycle as in the soil temperature, but you can like also slowly watch its dynamics there. Here you see another result where we basically already what I had a little bit sketched in the loop before, another coupling also to speedy weather, where we basically in between had already a downscaling. Basically, we're taking a relatively coarse state from the atmosphere, we're downscaling it to a more finer resolution, then gave it to Terrarium, and then we basically fed it back in. This was there done just with a very simple bilinear interpolation, but in the future we also might replace this with a diffusion model for the dynamical downscaling. There you see the air temperature, soil temperature, evaporation, and the surface humidity of then the coupled land atmosphere system. Yeah. One other thing that we also care about, as I said in the beginning, is the differentiability, and there we can rely on both enzyme and also on reactant. And to run our model with reactant, we just literally have to change one line of code. We just have to tell it that we want to run with reactant as the device and the architecture, and then our model runs with reactant. Everything else is done behind the scene. In our repository, you can already find a tutorial on how to do also online and offline learning with neural networks with this. But this is really more like a synthetic toy example there. So I don't have any like nice results here to show yet there. Something that I could show you just as one figure from this is here sensitivity analysis, a parameter sensitivity analysis of the soil temperature with respect to the heat conductivity there. And there you basically see the largest sensitivities where we're basically close to a phase change from freezing to liquid, where we will then also physically expect the largest sensitivities to my understanding of the physics there. Okay, but to wrap up, what we still have to do is that, of course, this is still very early in its development, and we still have to add more features. This is especially things from the vegetation model are missing, but we also have to improve the time stepping a little bit, where we can also, for example, use some of the tools of our shenanigans for implicit time stepping very easily. Then we have to continue a little bit with the integration into numerical Earth for coupled simulations. We have to also evaluate the model a bit better against observations and standard benchmarks, and really basically also start to experiment with the hybrid modeling a little bit more. Yeah, you can find our repository there and our contact emails there. Thank you very much. Yeah, the question was about lateral transport and how we envision that. So at the moment, this isn't present. And of course, you're right that also tools like our shenanigans can certainly do this. So we basically have tools available. This is on the roadmap, but at the moment, not very high. So in some point, we have to address this, of course. And we have also, with something like our shenanigans powering this, we have also like tools for this already available. But we then have to rethink also a little bit how we deal with the grids. And like, yeah, we have to figure some stuff out. And there are a few other priorities before this to really address it. There's like the soil model is yeah, it was the question was about the soil model. The soil model is based on the Richards equation, the basic implementation that we have there. About the freezing, to be honest, I can't really tell you. This is why maybe you should Brian a message or look in the repository, because I'm really not the soil modeler in this endeavor. He could tell you a little bit more about this. Yeah. And the question was about whether we could use the model about looking at permafrost in the Arctic. And I think we can, but this is also something that you should really also maybe shoot a message to Brian. He's the permafrost modeler by training in his PhD, and he would basically, if you have some ideas there and something that we can do there together, then I think he would love that.
Thank Max and Brian again.
Okay, next up we have Benedict Geijer, who is going to present some cool atmospheric modeling with discontinuous Calgarian.
Yeah, great. Here we go. Yeah, thanks a lot. So this will be about Trixie Atmo, which is a spin-off package of Trixie.jl. And yeah, I'm just one of many contributors here. This list is not even complete. And I'll try in the short time to give a rough overview of what we did in the last years, actually. The first release was in January. and why we think that this is a special package, kind of. Um, so we are actually not, we have not been for a long time in this business, but when we entered, we kind of picked up this general paradigms that you want to increase resolution, so aiming towards kilometer scale, with the idea that you can then resolve more processes and gain a better understanding of the Earth system. And because of our background in Trixie.jl, which is a discontinuous Galerkin method, we of course thought, okay, maybe that would be a good idea to apply this to the atmospheric flows as well. DG has very nice conservation properties. It is a high order method. People will typically show you these nice convergence plots. But you can also make this very robust nowadays, and that's actually the central feature of Trixie.jl, where entropy enters as another conserved quantity, and that can really stabilize your simulations. It comes at a certain cost, but the arithmetic intensity is primarily very local, so it scales very well. Yeah, and that's it. And the other idea that we had was why not apply dynamic adaptive mesh refinement? So just imagine a volcano would break out somewhere north of Europe and would pose a threat to air traffic or whatever. Then you could actually focus on tracking these ash clouds while being very coarse in the rest of the world. So two independent concepts, but they actually work quite well together. And I think they share the same fate, meaning they have not been adopted that much in this community, I think. Okay, so three very important points here that I need everyone to take home. And I will try to do this based on just one example. And that is actually one of the first test cases we implemented. And we could directly implement this in Trixie because we had the two-dimensional compressible Euler equations already there. We just needed to add a gravity term, idealized hydrostatic balance as an initial state. And yeah, then we could already let this run. So this is the classical buoyancy test case. You see this blob of warm air moving horizontally, but also due to buoyancy moving upwards. You get this nice plume shape and these rotors. And yeah, that result was actually obtained using Trixie and polynomial order 3. That means in 2D, in each cell, you now have 4 DG nodes in each spatial direction. So on such a cell, you have 16 degrees of freedom, but you can then run this test case on a pretty coarse grid. And if you compare this now to a low order method, and polynomial order 1 is the lowest we can do in Trixie, you just have 4 degrees of freedom on each cell. So to be fair, we here increased the resolution with respect to the cell count. So in the end, you have the same amount of degrees of freedom, but as you can see, the result is way worse. If you stick to such a low order scheme and just increase resolution, you get a little better, but not quite. If you increase once again, you are almost there. But at that time, you have used 16 times the degrees of freedom. So that would be the first take-home message. If it works, then you can really get a better resolution for less degrees of freedom. Second thing, I already mentioned the entropy stable schemes, and that was actually obtained with such a scheme with the flux by Henrik Ranocher. And if you compare this to the classical weak form, you will see you already get these bright spots down there, some disturbances where the physical sensible range actually is overshoot. And these disturbances could actually, in the long time, crash your simulation. So that would be the second point. This entropy stability can actually make your simulations run more stable. And third aspect, once again, here was a reference solution, and now we cut the degrees of freedom by a factor of 5, and that was done using AMR. And the reason, of course, is that here with a nice indicator, we could actually just capture the perturbation, and then you get these nice compression rates by AMR. So this was the concepts we wanted to bring into simulating atmospheric flows. And it was pretty clear that we could not just do it in Trixie because Trixie is a very generic framework. So we built our own spin-off package, and this is now Trixie Atmo.jl. And what we did so far is the following. So we started with the Cartesian world. That is what we were used to. But we also added a covariant formulation. So in a covariant formulation, you actually solve a PDE on the surface, meaning on the sphere here. That means you have to map your reference element to your surface or to your manifold, and then you have to fight all these metric terms. The reason primarily was that is actually what is being done in ICANN. And on this, with this covariant formulation, we first started with shallow water, but nowadays we also have Euler equations running. We needed to add further element types, in particular triangles and prisms. And of course, we had to set up some grids, cube sphere or the icosahedral grid here. And this is actually the barotropic instability, which you see here. In this setting, in the covariant setting, we also had to now derive new entropy stable and entropy conserving schemes. And for the covariant formulation, this was done in this paper by Tristan. And this graph here is from his paper. It shows results for the Rossby-Horwitz wave. And the situation is, so when you run this test case with standard DG, after about 7 days, you will see that entropy goes crazy. And at that point, your simulation will crash. So with these entropy conserving schemes, entropy is conserved. And in orange, if you just add a tiny little bit of dissipation, then you can get an entropy stable scheme, which lets this test case run, not forever, but for even longer. Same situation for the Cartesian world. So here the baroclinic instability test case turned out to be our favorite. Here we also implemented new variants of the Euler equations. So we were kind of looking for the primitive equations because for us it was not really clear how they would look like. So we have total internal energy, but also potential temperature and just internal energy. And in these papers here by Marco and co-authors, 2 of them in the last 2 years, they implemented, or in this setting, also new entropy stable and entropy conserving, but also well-balanced schemes. And the situation here was kind of similar. So everyone would typically show the picture for day 10. If you just use standard DG, it will crash about after 7 days. And Marco was able to run this up to day 20, I think. And here we could actually also run this with adaptive mesh refinement, which brings certain additional troubles because of the non-conforming interfaces which we have here, because that is the way adaptivity is handled in Trixie. But with these stabilized fluxes, we were actually able to do it also beyond day 10. What was still annoying was time step restrictions. I think it was already mentioned. So Trixie has always used explicit time stepping, but because of the vast differences in the horizontal and vertical scales, this is a real severe restriction here. So people started working on mixed implicit and explicit methods. We also added bottom topography. I think the expert was already here in the previous session. And in the covariant formulation, this immediately turns into terrain following coordinates. And finally, we had some first experiments with adding further species, in particular vapor and cloud water, but also rain, and now had to couple to a certain microphysics models. Just a few remarks on performance. Performance was always key in Trixie. So already in the past, we showed, or that was shown, that Trixie can actually compete with its highly optimized Fluxo predecessor. Sorry, Fluxo is a predecessor, and it is a highly optimized Fortran code, and Trixie is on par with it. In a very recent publication, we showed strong scaling capabilities on up to 60,000 ranks. And recently, we started to port our code to GPUs. We also used kernel abstractions. It has been mentioned several times, I think. We could actually run on up to 1,000 GPUs at Jülich Supercomputing Center. And then we had access to the Jupyter early access program, where we could run it on Jupyter hardware, meaning you have the NVIDIA super chips, 4 of them per node. And there we could run on up to 128 GPUs and were at least able to achieve a weak scaling efficiency of around 94%, which we were quite happy with. So to wrap up, what we have by now is we have our high order DG method. We have it in a Cartesian and in the covariant formulation. You can do it in a very robust fashion using the entropy stable fluxes in Trixie. We have some adaptive mesh refinement. We applied this to, let's say, synthetic problems in atmospheric flow, atmospheric science. It is actually HPC capable. What we're currently working on is the mixed explicit and implicit time stepping. We're currently bringing AMR to the GPUs as well. And we started with HealPix grids. I think you have seen a nice picture of that as well. What we're currently looking for, what we really would like to have, would be to go more realistic. So start from reanalysis data, but for that we would need something, yeah, some working conservative remapping package. But actually, I think this morning I heard about a package which is called conservative remapping.jl. So maybe that could be a game changer. Some ease of life, data analysis, statistics, visualization, maybe in situ or post-processing would be very nice to get more nice videos as we have seen before. And also, yeah, we are looking for other package we could couple to get more parameterizations, for example, for microphysics. So details on this, but for now, thanks for your attention. That was the polynomial order, right? Yes. So I'm sorry. So the question was about the polynomial order on the elements we would typically use, or the largest one. So our typical setting would actually be p equals 5. So the baroclinic instability was one with polynomial degree 5. In principle, you could go higher, but I think p equals 7 was the largest choice I made. Yes, that's correct. Yeah. When we were about to do our scaling tests, that was actually something we tried out. Yeah. Strong scaling actually worked quite well with polynomial degree 5. But yeah.
Next up is Sujan Karala from IENA. The floor is yours.
Thank you. Yeah, thank you for having me. I'm going to bring you back to land. So, as always, this doesn't work as expected. Let's see. So, I'm going to talk about the framework that we've been developing in our institute for long. It's called Sinbad. It's a modeling framework, and it's not just one model. I think it's actually the same motivation of playground for modeling Lego, but for terrestrial ecosystem. This is why also you see the figure here. When you think about a modeling system, a model is a combination of processes which you drive by input, has parameters, there are initial conditions, and you somehow compare it with observation. And all of these, you have different choices. That means these are also sources of uncertainty, and you would like to build a system where you learn from the observation which the best model structure is. So this work was not done in a year or so. We started with around 2014, build a framework until 2021 in MATLAB. Then around 2021, we decided to port the conceptual part of it. So it was not a translation, build everything ground up in Julia. And in like around 3 years, we managed to release it. A couple of years ago, Lazaro made the presentation for one of the examples that I will show. But now, at this moment, all these packages are in registry. You can get them anytime you want. And it's not only one package. So there is a big Sinbad.jl package, and it uses Sinbad-TEM, which is the core modeling framework that we have. And we have tools that we use in the modeling that are separated and made independent into Omni tools. We have error metrics that we use to measure the performance of the model against observations. This is also an independent package. And we have time samplers that you need. Sometimes you have model in daily scale and the observation in monthly scale, then you would want to do this aggregation on the go so that you can compare the model and observations on the go when you are doing parameter calibration. And all of these are, as far as possible, allocation free. They run very fast. They are very efficient. So at the core, we have the Sinbad terrestrial ecosystem model. It's basically a collection of formulations for different processes. They all come down from a very abstract land ecosystem type. And for example, the process to separate rain into rain and snow, the precipitation into liquid and solid form. You have different approaches to do it. And as you go to the approach level, it's becoming really concrete type with parameters like it was shown before also in other models very similar to them. Here is a threshold, and if the threshold is below something, then you make it a snow, otherwise you make it a rain. And the advantage of writing the models in this way is we can always rebuild this struct using different values of the parameters. That is really key to changing the parameters, tuning the parameters on the go. So in total, this is one example. We have 87 big processes and multiple formulations for each of these. So we can technically have a model intercomparison with one framework. And the Sinbad JL itself is the orchestrator. So it takes in the data, does the setup of the model, and it loads the data, does the simulation, does the experiment, and whatever you need. But in practice, you just look at, you do using Sinbad, you have a settings file where you list all the model structure, you list all the observations that you use, and also the metrics that you want to measure the performance of the model. Then you basically load this forcing using the same information that is already typed into whatever the model can understand. And at this point, you just do the runtime, and no matter what the scale is, what the experiment is, you just call it the same way. So you don't need to change the way how you do things. But compared to the examples before, you have only few models. In Sinbad, you can have any number of models. So this is actually done through the settings and not directly in the code. You could do it that way as well. And I think one thing that we benefited in the last years is from having the extension and weak dependencies. That means the inner big Sinbad for basic experiments are very light. Good. So I'm not going to go into detail of every model, but basically you can build different model structure based on the scale and the objective of your science. It's always driven by science. The bigger model here, the simplest one is the global model. You see that there is not many soil layers. The vegetation is inactive. You can go to regional scale, make it a bit more complex with active vegetation, water, carbon coupling. At the site scale, where you have more data, you can also do carbon explicit through transport through different pools, coupling at different levels. So in all these experiments, what we did is we calibrate the model parameters. This is easier said than done. At the site scale, it's fairly easy, but I think we were one of the first models to actually also apply it at the global scale. This was already done in the MATLAB version. There are many, many papers explaining how we could do, I think, better than most of the models that you see globally. But that makes sense because we use the observation to do the calibration of the parameters, right? So the main question and also the focus here is what we actually gained from having a Julia-based framework, because we already had spent 7 years doing things, right? So I think in one sentence, it gave us opportunities to push the boundaries. So first example that I want to show is it's differentiable, of course. And 2 years ago, I think Lazar made this presentation in JuliaCon, where he showed that we can actually train the neural network online with the physical model to learn the spatial variability of the parameters. What you do is you have a bunch of features, you put it through the neural network, it will give you a set of parameters that you put and run the models with, then you get an output of X different variables, which you also have observation for, then you measure the performance against the observation, and based on the gradient of this loss, you update the neural network and get new parameters. So we are learning not only parameter per site, but also its spatial variability. And the second thing that we gained was solvability. I think no one talked about the spin up today, but spin up is really one of the biggest burdens. Here I saw different carbon pool in x-axis, their sizes in the y-axis. Blue is the initial point. Red is the line where you would reach if you run 1,000-year simulation. So this takes around 1.5 seconds because our model is relatively fast. And if you were to use a root finder solver, you would reach the green line. And at this point is the steady state solution. So if you run the simulation after that, there will be no change in pools, which is the purple line. So we can get, even for the slowest pools in 0.2 seconds, the steady state solution. And this is really a game changer. We don't need to run 10,000 years to get the steady state. We can get it in few seconds. And the second thing is parallelizability. This, I think, on the left is a typical climate, I think, state of the art. This is quarter degree data. This is 50-kilometer span somewhere in Australia. This is rainfall, climate on the left. On the right is a high resolution remote sensing data where you see that there is a lot more structure and variability in the land than in the climate. So if you were to run everything based on climate, you would get something like this output. But using remote sensing together, we can do that. This is different carbon pools. You can get really a lot more structure into your model simulation at 350-meter resolution. Not only that, you also see the differences across different pools because we have different dynamics and processes there, right? And this one takes 1 second. We can do it globally. This is Reaxer is lazy run. So hopefully we'll go to some 300-meter simulation globally in the coming months. And the last thing that I want to say that it also gives us a lot of chance to extend an opportunity to bring it together with other packages. There has been many talks about Speedy Weather and Terrarium. We want to replace some of the carbon processes in the Terrarium because you can call Sinbad time. Really, without all the orchestrator, you can call the core of the model and you can replace the processes in any model. This one, we agreed that it should be easy. We have not managed to do it yet. ClimaLand also is the same when you look at fundamental things because we depend on name tuple that is really native type. We can also couple it there. This one in the last weeks, actually we built a prototype we could call Sinbad process from within ClimaLand and it was able to exchange the data and do the forward route. So this is something that is really good for us. So to take home, we have always done the modeling with application-centric development rather than software development things, but it's still very performant, which is really nice. And Julia has been an enabler. I'll not go into the details here. I'll just say thank you. And if you want to get involved, it's, I think, relatively well documented. You can go there, you can talk with me, Lazaro, anyone from the Institute. And that's it. Thank you. So the question was if there is a possibility that we can do the actual plant growth within this framework. And actually, I think there is an abstraction of plant growth within the model. So what we do is when there is assimilation of CO2, we actually have growth into wood and different components that die off. So there is an active growth model inside. We don't depend on PFT. We really don't agree so much with the PFT concept of having classes of vegetation. So we tend to let it grow and also let it die when there is a process, when there is a active coupling between the resources and the demand. And that way we in a way, we do that, but beyond, like we don't do leaf scale processes and so on. But there are works to put more mechanisms like plant hydraulic failures, and these things are already in place. We are running this at sub-daily scale, so we are putting in different mortality processes, maybe some management in there as well. So we are going towards it, but to do an actual plant, I think we need to, also maybe it's a philosophical question that we can talk about later. Oh, okay. There, technically there could be. This is also, again, going back to the lateral transport. So when you start talking about landscape and when you go to higher resolution, you need to start thinking about these processes. So there are some packages in Julia which do this kind of dispersion very well in space. And also for land, if you want to do topographic and landscape scale variability, we need to do it. So hopefully we can be able to plug in these things with wind and so on.
Thanks again. And we now welcome a local PhD student, right, from Mainz, Pascal Eilich. The floor is yours.
Okay, thank you. We're gonna switch the regions from or above surface modeling to subsurface modeling using Just Relax. This is a Julia package we've been developing for the last, let's say, 6 years in the framework of 2 or 3 funding schemes, PUSC, GPU for Geo. You will probably hear in later talks or are already familiar with, and the ERC project Magma, which I'm funded from. So the solid Earth is also not different to the atmosphere. You need to compare your results to physical constraints from petrology, so the rocks, the geophysics you measure either through seismic waves or inversions of the mantle, and through geochemistry. And for that, you also need fast codes that both run on your laptop and on the biggest supercomputers. And with this, in the last 15 or let's say 10 to 15 years, the geodynamic community has mostly relied on CPU codes, and they have a lot of different packages and methodologies. For example, Underworld has 300,000 lines of code, and on top of this uses PETSI, and everything else also has tens of thousands of lines of code, and they all are CPU optimized and not GPU. And as you probably all know, the modern supercomputers will move to GPU and slowly, but slowly abolish the CPUs on the computing side. And so what does a geodynamic code in Julia actually need? So first of all, the physics. For that, we rely on a package called geoparams, so the geological parameters where all the material calculations are based. And for the material advection, we use a particle and cell or marker and cell advection schemes that rely both on cell arrays and kernel abstractions to have it ported for both CPU and GPU. The parallelism within Just Relax is done twofold. One, through parallel stencil, which is backend agnostic, where you can run it on CPU, CUDA, AMD, and even Metal, but currently Just Relax does not support this due to some method issues. And also Implicit Grid, which does the MPI handling and is natively coupled or easily coupled to parallel stencil. And on the visualization side, we rely on VTK, HDF5, and JLD2 for checkpointing and visualization, especially for the 3D models. We published a paper on this in JOS in the beginning of the year, so if you're interested, check it out. So the method behind Just Relax is a matrix-free Stokes solver, so we neglect the inertial terms and only solve Stokes, where we augment the left-hand side with a so-called pseudo-transient. And these are, they're these terms where we solve them explicitly until this is until this reaches a tolerance, and we can say that it has converged. We use a staggered grid, finite difference discretization, as I already said, a marker and cell advection scheme, and we are able to have very nonlinear rheologies through the native support with geoperms. The methodology is pseudo-transient, either the accelerated pseudo-transient or the accelerated pseudo-transient with a so-called automatic tuning, where we estimate these damping coefficients on the fly, because if the physics change, then these damping parameters also change. And because we are Julia based and there's this nice package you all probably are familiar with called Enzyme, we can differentiate our model. We have good algorithmic scalability across hundreds of GPUs. We ran on the Swiss supercomputer in Lugano. Strong scalability is good up to 64 GPUs and drops from 256 onwards as it is expected because we underload the GPU. On the weak scalability side, we show, or we have a rather good scalability for 3D and also quite nice scalability in 2D. I don't actually have a reason why we have this drop at 64 GPUs, potentially node health. And something I talked about already is the automatic tuning. And if you see the difference between the accelerated pseudo-transient and the automatic tuning, the iterations it takes for the solver to converge stays linear for the dynamic or auto-tuning, whereas for the pseudo-transient, it fluctuates depending on the physics. So applications, in general, the rocks in the subsurface are viscoplastic, so they can break. And breaking the rock is hard numerically because it adds singularities and it does not like to converge to a nice solution. There has been progress in the last decades on how to solve this numerically, and by basically augmenting the plastic rheology with a viscosity that dampens this effect. And because we have native GPU capabilities, we were able to actually run fault localization benchmark with a weak inclusion in the middle and pure shear boundary conditions on 64 NVIDIA Grace Hopper superchips, and have a grid resolution of roughly 41,000 by 41,000. And if you only count primary variables like velocity and pressure, you actually end up at 5 billion degrees of freedom. And to our knowledge, this is the highest ever viscoelastic plastic benchmark. And if you zoom in, you can actually see how the pattern like repeats itself and the fractal nature of fault systems is retrieved, which is not possible in lower resolution models. Okay, to end up, as I said, you can see how the fractality of these models are increased with resolution. So take home message, developing a modular GPU accelerated code in a user-friendly language must be the goal for the geodynamic community. We achieve good scalability with a GPU-friendly method and relying only on the Julia ecosystem. We, as I said, have the highest brittle deformation model in the solid earth to date in 2D. As an outlook for the 3D solvers, we we'll try to implement geometric multigrid and further develop the differentiability of just relax through enzyme or potentially reactant. And with that, thank you very much.
Do we have questions? I might have one. Is resolution such a limiting factor nowadays in geodynamics? I mean, do we really want to go much, much higher? Do we need that to answer scientific questions?
If you think about the normal geodynamics, there's a centimeter scale, so the higher resolution, the better, but it also depends on your question you want to ask. If you only are interested in a subduction zone, then probably a kilometer resolution is fine if your model domain is 600 kilometers. While for crystal size model, you want the resolution. Thank you.
Maybe one last question if it's quick.
Yeah, in your scaling, 1024 GPUs was a drop in efficiency. Do you know where that's coming from? Do you know the source?
Yeah. From my question was why we have a drop in the strong scaling at 1024 GPUs. I think it's just that we underload the GPUs and this slows down computation because it's actually at 464 that's near perfect. Then we do not increase the resolution on the GPU. Thank you.
Yeah, thank you very much. So next up, we have some hybrid flux partitioning presented by Bernard.
Yeah, thanks a lot for the intro. So yeah, we will look on learning the temperature sensitivity of ecosystem respiration with our package easyhybrid.jl. And while looking at the results, I will also show you how you can use this package in general. So what we're looking at is the carbon balance of an ecosystem. So what we want to know is, for example, is the system a carbon source or a carbon sink? So the two most important growth fluxes are photosynthesis, which we also call gross primary productivity or GPP. We have the respiration losses, which we at ecosystem level call ecosystem respiration, or in this talk, I often refer to it as RECO. And then the balance of these two fluxes is the carbon balance, or we call it also net ecosystem exchange, NEE. NEE we commonly measure with eddy covariance towers. So we can only measure NEE, but not the gross fluxes. So what we want to do here is we want to partition NEE into GPP and RECO, yeah, to identify the driver of carbon sink and source shifts, for example. And we want to look at the temperature sensitivity of RECO to quantify how respiration might respond to warming. So in general, there's three easy steps that you can take with easyhybrid.jl to define a hybrid model. So you start with defining the mechanistic model. In our case, it's a simple light use efficiency model with a Q10 formulation for respiration. So we have here GPP as a function of shortwave incoming radiation and a radiation use efficiency parameter and some unit conversions. And we have RECO, which is comprised of a basal respiration parameter and a Q10 temperature formulation. So Q10 is another parameter. And then we have NEE as our final output. And then the most important part in Easy Hybrid, so we have all these parameters. In the model, you have to decide which of the parameters you want to train context dependent, so that would include then a machine learning component, and which ones you train as a global parameter. And you can also, of course, prescribe parameter values. So in our case here, we decided that we have the base respiration and radiation use efficiency as context-dependent parameters. And we feed these covariates into the neural network, so soil water content, and then different variants of potential shortwave incoming radiation. For radiation use efficiency, we have additionally air temperature and vapor pressure deficit. Easy Hybrid is built on top of LUX. And kind of the most important step then is to construct our hybrid model, where we give the names and of the context-specific parameters together with their covariates. We say what are the names of the forcing in the data frame. So we have two forcings here, shortwave in and air temperature. We specify the target. So in our case, it's NEE data. We give the mechanistic model. We have parameter bounds, which I didn't cover in this talk, and we say which of the parameters are global parameters, so which are estimated globally. If we didn't have the Q10 there, it would be fixed to a default value. And you define the hidden layers, the neural network that is used to describe RB and radiation use efficiency. We take care of the input layer and the output layer for the user, so you don't have to think about how many outputs you have and how many inputs you have. So that's adapted automatically. And then the third easy step is to train the hybrid model on a data frame. So here we have the eddy covariance data in a data frame, and you use you have the classical arguments on kind of machine learning or neural networks, number of epochs, the batch size, which optimizer you want to use, what the loss function is, and then additionally we have here which parameters you want to monitor during the training, so that we maybe not only want to look at the loss and validation loss, but also at the evolution of these parameters. So that's what I show here. So in Easy Hybrid, you can monitor the training interactively in a dashboard. And if you want to know more about that, I guess you have to ask Lazaro, who is a big contributor also to the Easy Hybrid package. And here you see a quick video sped up a bit for the training process. So where you have training and validation performance, a scatter plot, and then here how the different parameters evolve over the training process. So in Q10 is a scalar, so it's only one value, and radiation use efficiency and basal respiration, RB, are output of a neural network. So there we then also monitor the quantiles of the output to get like an idea how these values evolve over the training. The question we wanted to answer, or we want to answer in this flux partitioning study, is to ask if we can estimate Q10 directly from raw NEE data. So before this has been done already on partitioned ecosystem respiration, but not on NEE directly. And we want to see if the temperature sensitivity, the Q10 estimates, converge cross ecosystems once we have accounted for confounding factors. So that would be kind of all these covariates. So we use data from a lot of EC sites, and as I'm about to wrap up, You see here that indeed we find a convergence of Q10 values across ecosystems. So that's here just across mean annual temperature plotted. And we also see that regardless of the initial value of the Q10 that's given in the at the beginning of the training process, we also have convergence with within this training process. So I think I skip over the purpose. I think you have seen it. I quickly acknowledge the funding and thank you for listening, and yeah, invite you to check out Easy Hybrid and contribute maybe if you have ideas what to do. Thank you.
We have questions? Maybe I can make a small one. So far, you really applied this to soil modeling, right? And to, but I mean, a priori, there is nothing that constrains it. That specific application.
Oh, it's not constrained to any application, so you can apply that to pharmacometrics, different types of ecological models. So here it was like just on ecosystem scale, so not specifically to soil. Yeah.
Well, thank you very much again.
Thank you.
Next up, we have Annalena Stroh.
Hi, I'm Greg. I'm a PhD student supervised by Milan, and I'm going to talk today about learning a surface roughness scheme for climate prediction in speedyweather.jl. So the surface roughness is kind of what it says on the tin. It's a measure of the roughness of the Earth's surface, both over the land and the ocean. And it's actually quite important. I hadn't really heard about it before I started this project, but it turns out that it helps govern the surface-atmosphere coupling in climate models via the boundary layer drag and impacts the surface fluxes, as you can see here. And in this presentation, I'm going to denote it as Z0. So if you see Z0, think surface roughness. And it's quite important, like I said. So there's studies that show that if you bring your surface roughness closer to observations by a little bit, it can significantly change your regional surface climate. So in this study, they found it changed it by up to 5 degrees in some locations. So getting this quantity right is quite important. Why would you learn it instead of explicitly modeling it? So ERA 5 uses lookup tables for the land surface roughness for both the M is for momentum, H is for heat, and Q is for moisture here. And it basically looks up depending on what type of surface tile is present. Not every climate model has the diversity of PFTs that we can use to like generalize, basically use this lookup table in all climate models. So and then on the ocean side, it's dependent on U star, which is the friction velocity. And U star is very complicated and expensive and needs to be solved iteratively at every time step. And so we have a bit of a wish list for modeling both of these over the land and the ocean, which is to basically build a spatially generalizable model from common variables, like variables that are common to lots of climate models. And then also over the ocean, make it spatially generalizable, physically constrained, and very efficient to run. So over the land, what we do is basically compress this table into neural network weights. So we train from ERA 5 data to predict both the momentum and heat surface roughness over the land, and give a bunch of different input variables that help the network discern between different land surface types, which I'll show here on the right. We did try other methods, so random forests, which had pretty similar accuracy to neural networks, but they were really expensive to run in the model when coupling to speedy weather or including this in speedy weather. We tried an XGBoost framework, but again, it was just too expensive, too memory heavy to run online, and then linear or ridge regression was just not accurate enough. So a neural network was what we went with, but then actually practically including this in the model at every grid cell, at every time step is pretty expensive. And so we went even further to try and distill the model from a small MLP, like order of 1,000 parameters, down to a single equation of order 10 parameters. And we don't really mind about uninterpretability as much here. And so we kind of let loose on the symbolic regression fitting complexity. So we use symbolic regression.jl for this task. But we still select the most optimal model from the Pareto front. And I don't know if you can see here. The model gets the symbolic regression model gets pretty good R squared compared to the teacher neural network, and also gets comparable R squared on the test data and comparable RMSE on the test data as well. So you kind of make this trade-off between speed and accuracy, and I think in this case it's sort of within our bounds. So then moving on to the ocean side of things. So what we want to do here is actually decompose this process into more modular or specific mechanisms. And as I said, this component, the friction velocity, requires iterative solving. And naively, what you could do is model this based on the actual wind. So you could throw the wind speed. So I should say, surface roughness of the ocean is determined by the wind speed. The wind blows over the water, and it generates ripples or waves. And what you could do is just throw the wind into a neural network, and the Charnock parameter, which is this ACH parameter here, which tells you how wavy it is on the ocean surface, and hope that the neural network does the right thing. But it actually leads to regional biases over stable and unstable boundary layer regimes, and that's because the physics over these actually matters. So if you have some combination of a cold ocean and warm air moving over the top, or warm ocean and cold air moving over the top, you get different wind speeds as a result of those thermal instabilities from those differences, and that actually impacts the surface roughness. And so what you could do naively is then you could make it a sort of mini super parameterization where you just throw in your wind speed, your actual wind speed, and these thermodynamic state variables, and hope again that the neural network does the right thing. But our hypothesis here is that because the thermal boundary conditions, like the temperature of the ocean, doesn't intrinsically relate to the surface roughness itself, it's not a causal variable, and so we don't think that it will generalize as well. So you get these unphysical correlations between the input variables and the output. And so what we do instead here is map the actual wind to the neutral wind, which is basically a quantity that asks what is the wind speed that gives me the same surface roughness but with no thermal effects, and then we use the neutral wind to predict the surface roughness instead. And that's what we do. And again, we train on ERA5 data and test, train on 2023, test on 2025. And this is open ocean, no sea ice. And so we throw in our actual wind speed, the temperature gradients, the 2-meter temperature minus skin temperature, and the temperature itself into a very small neural network, just order of 100 parameters to calculate the neutral wind speed. And then we again distill this via symbolic regression so we can actually run it online in the climate model. And we get out from that this quite interpretable expression. This is our map from our neutral wind to our actual wind plus this correction term, which is what our model is trying to represent. And on the bottom, we actually can see we've got a correction driven by mechanical shear here, which basically says that if the wind speed is really high, our correction goes to 0. And this is kind of supported by the equations that this data is generated by. And also, you can see just empirically here where the actual wind speed and neutral wind speed at high wind speeds, the difference is negligible. And then at the top, I'm not going to go into details, but we have our sort of thermodynamic terms of correction for sensible heat flux for when you have a high stability regime and latent heat flux correction. So then we want to model the surface roughness from this. So we throw in our neutral wind, our Charnock parameter, which is our sea surface state. And we actually make this a stochastic model by feeding in a Gaussian field along with it, so a 1D Gaussian field. Into our MLP, which is again order of 1,000 parameters to predict both the momentum and heat surface roughness over the ocean. And during training, we train with the CRPS, the continuous rank probability score loss function, to generate 50 ensemble members during training. And then again, once this model has been fit, we distill it with by using symbolic regression.jl down to a very small equation. And we get this sort of stochastic symbolic expression out the other side because during training, again, we redraw these samples from the Gaussian field every single training epoch. And the MLP basically learns to project the inputs onto the target distribution by generating this ensemble. But once the training's done, those weights are frozen, and so we have a map from from any Gaussian input to our target distribution. And so we do a single forward pass of our neural network to generate all the training data to then fit our to fit the symbolic regression too. So here on the left, I've got the deterministic fit. So I just take the model ensemble output and fit use symbolic regression to do a fit. This is useful because if you want to run online in speedy weather, you need to use a sort of a 2 or 3D Gaussian field if you want to use the symbolic version, if you want to use the stochastic version, but maybe you don't always want to do that. So this is the deterministic version. And then on the right, we've got the stochastic version with the Gaussian field as input. And you can see that below wind speeds of about 10 meters a second, it really starts to make a difference. We get better coverage of the distribution of surface roughness. Here, this is surface roughness on the y-axis and neutral wind speed on the x-axis here. And then the same story goes for the heat surface roughness, where again the stochastic expression has better coverage of the distribution of surface roughnesses as well. And again, well, not again, but we go further. We apply this physical limit because we want to be able to extrapolate into warmer climates where we might have higher wind speeds and more intense storms. If you did not apply this limit, you can see the gray line, the expression for surface roughness just goes way off. So you have infinitely increasing surface roughness with winds. That's not physical. We actually don't understand this completely, but what most climate models do, they'll impose a physical cap and then taper down again at higher wind speeds. The takeaway here is that basically this is a 1D, this is like a grid cell specific MLP. There's no spatial dimension to this, but we can recreate the spatial patterns over both the land and the ocean. So we know our neural network and our symbolic regression is doing its job correctly. And these are just the maps, prediction on the left and then truth on the right. And then we've got our error maps here as well. I'm going to wrap up. I'll leave you with some simulations online from Speedy Weather. The top is the learned and the bottom is the default version. Thank you.
Yeah, sorry for cutting you off. We have to go for the group picture, which is now in front of the Alte Mensa. Thanks for everyone for attending, for talking. It was extremely pleasant. Just a small note that after the photo, there is the keynote. And after the keynote, whoever wants to go for dinner is invited to join with us in front of the Muschel, so in front of the current building. Okay, thank you very much.